Right now, as you listen to this, around 3 million of your red blood cells are dying. 3 million. Every single second. They are breaking apart inside your body, crumbling into fragments that your spleen is quietly filtering out of your bloodstream while you lie here, breathing, thinking, being you. And 3 million new ones are being made, right now, deep in the marrow of your bones, slipping into your veins like fresh recruits replacing fallen soldiers. You do not feel it. You never have. But by the time you finish listening to this sentence, millions of cells in your body will have been replaced by cells that did not exist when the sentence began. Your skin is shedding right now too. The outermost layer of your body, the layer that the world touches when it touches you, is made of dead cells that are falling away, invisibly, constantly, like leaves from a tree in slow motion. In about 2 to 3 weeks, the entire surface of your skin will have been replaced. The hand you see in front of you will be wearing an entirely new glove of cells. Your stomach lining replaces itself every few days. Your liver takes about a year. Your skeleton, the hard frame that holds you upright, is being dissolved and rebuilt by specialized cells, and in roughly 15 years, every bone in your body will have been remodeled. Even the atoms themselves, the carbon and oxygen and hydrogen that make up these cells, are constantly being swapped out, cycled through food and water and air, replaced by atoms that were recently part of a tomato, or a cloud, or the breath of a stranger on a train. Think about what that means. The body you have right now, the one pressing against the mattress, the one breathing this slow breath, is not the body you had 10 years ago. Almost none of it is. You have been rebuilt, piece by piece, molecule by molecule, without ever being taken apart. You are, in every physical sense, a different person than you were, and yet you feel like the same you. You remember your childhood, even though the brain that stored those memories has physically changed. You recognize your own face, even though the face in the mirror is made of entirely different atoms than the face that was there 5 years ago. So here is the question that is going to carry us through tonight. And it is a question that sounds simple, but the deeper you go into it, the stranger it gets. If every part of you is being replaced, constantly, relentlessly, cell by cell, atom by atom, what makes you, you? What is this thing that persists, that feels continuous, that wakes up every morning and says, I am still me, even though the physical stuff it is made of keeps changing? Is there something at the core of you that stays the same? Or is the very idea of a permanent self an illusion? A story your brain tells to make sense of the endless flow? And that is just the beginning.
Because when you start pulling at this thread, when you really start asking what you are made of and how that stuff behaves, you discover something even more unsettling. The atoms in your body, the ones that are being swapped in and out, are not what they seem. They are not solid little spheres. They are almost entirely empty space. And the tiny pieces inside them do not behave like objects at all. They behave like probability waves that only become definite when something interacts with them. And the time that seems to flow around you, the steady tick of seconds carrying you from past to future, that is not what it seems either. Time does not flow at the same rate everywhere. It bends, it stretches. It depends on how fast you are moving and how strong the gravity is around you. Your feet, right now, are aging at a slightly different rate than your head. The difference is absurdly tiny, but it is real. It has been measured.
And if time itself is not steady, if the very clock of your existence runs differently, depending on where you are in the universe, then what does it even mean to say that you are the same person from one moment to the next? Tonight, we are going to take this apart, all of it, slowly. We are going to start with your body, with the ancient philosophical puzzle of what makes something the same thing when all its parts have changed. And from there we are going to go deeper into the atoms that make you up, into the quantum strangeness that lives inside those atoms, and into the nature of time itself, which turns out to be far more personal, far more flexible, and far more mysterious than anything you were taught in school. We are going to trace a thread that runs from the cells in your body to the fabric of space-time itself. And by the end, you might see yourself differently, not smaller, even though everything we discover will make the solid world seem less solid, but differently, more surprisingly, more wonderfully. There is no rush. We have the whole night. The room is dark or darkening. Your body is settling into the mattress. You can feel the weight of the blanket on your chest, the subtle press of gravity pulling you down. The same gravity that, as we will discover, is actually bending the very fabric of time around you at this exact moment. But we will get to that. For now, just breathe. Let your breathing slow down. And let us begin with a ship. There is an ancient Greek legend about a ship that belonged to the hero Theseus. Theseus was the mythical king of Athens, the one who sailed to Crete and killed the Minotaur in the labyrinth, and then sailed home on this ship. The Athenians loved that ship. They kept it in the harbor for centuries as a memorial, a physical link to their greatest hero. But wood rots, salt water eats at planks, ropes fray. So over the years, when a board decayed, they replaced it with a new one.
When a mast cracked, they put in a fresh mast. When the sails wore thin, new sails went up. This happens slowly, over generations, one piece at a time, until eventually, every single part of the original ship had been swapped out. Every plank, every nail, every rope, every inch of timber was new. Nothing that Theseus had actually touched remained. And the philosophers of Athens looked at this ship sitting in the harbour and asked a question that still has no clean answer 24 centuries later. Is it still the Ship of Theseus? You might say, well, of course it is. It is in the same harbour. It has the same shape. Everyone calls it the Ship of Theseus. The name stuck. The purpose stuck. The story stuck. So what if the planks are new? But then imagine a twist. Imagine that someone had been collecting all the old planks, all the rotten nails, all the frayed ropes, every discarded piece. And imagine that this person rebuilt the original ship from all those original parts. Now there are two ships. One made entirely of new material, sitting in the harbour, called the Ship of Theseus. And one made entirely of the original material, sitting in a workshop somewhere, looking a bit worse for wear. Which one is the real Ship of Theseus? The one that has the continuous history, or the one that has the original stuff? This puzzle might seem like a game, a trick for philosophers to argue about over wine. But it is not. Because this puzzle is about you. Think about yourself for a moment. Not abstractly, not philosophically, but physically, biologically. Think about the cells in your body and what happens to them over the course of your life. A red blood cell lives for about 4 months. That is it. 4 months of circulating through your veins, carrying oxygen from your lungs to your tissues, and then it is done. It gets old, it gets stiff, it cannot squeeze through the narrowest capillaries anymore, and your spleen catches it and breaks it down. The iron gets recycled, the rest gets flushed, and a new red blood cell, born in your bone marrow, takes its place. This happens constantly. Your body is making about 200 billion new red blood cells every single day. Every single day. That number is so large that it is almost meaningless to say out loud. 200 billion. And just as many are dying. Your white blood cells have even shorter lives, some of them. Certain types of white blood cells last only a few days. They patrol your body, looking for invaders,
and when they find one, they often destroy themselves in the process. Your gut lining, the cells that line your intestines, replaces itself every 3 to 5 days. Your skin cells take about 2 to 3 weeks to cycle through. The cells on the surface are already dead, just waiting to flake off, while new ones push up from beneath. Your liver is a slower rebuilder. It takes about a year to turn over most of its cells. Your bones are slower still. About 10 years for a full remodeling cycle, though it varies. The lining of your lungs replaces itself over several weeks. Your taste buds last about 10 days. Even your skeleton, the hardest, most solid-seeming part of you, is in constant renovation. There are cells called osteoclasts that dissolve old bone, eating tunnels through the hard tissue, and other cells called osteoblasts that fill those tunnels back in with fresh bone. The whole process takes about 10 years for a full cycle, and it goes on your entire life, keeping your bones strong, adapting them to the forces you put on them. So almost everything about your body is being replaced, constantly, silently, without any conscious effort on your part. If you are 40 years old, your red blood cells have been entirely replaced about 120 times since you were born. Your skin has been replaced roughly 700 times. Your gut lining has been replaced thousands of times. But there are exceptions, and the exceptions are fascinating because they reveal something about the boundaries of the puzzle. Your neurons, the nerve cells in your brain, are largely permanent. You are born with most of the neurons you will ever have, and with a few exceptions in certain brain regions, those neurons stay with you for your entire life. They change constantly, forming new connections and pruning old ones, strengthening some pathways and weakening others. The structure of your neural network is in constant flux. But the cells themselves, the individual neurons, are mostly the ones you started with. Your heart muscle cells are also mostly permanent. Some of them do get replaced, very slowly, maybe about 1% per year when you are young, dropping to less than 0.5% when you are older. But the majority of your heart cells are with you from the beginning. There is something else too. Something quieter and stranger that happens in your brain even though the neurons themselves persist. Your brain is constantly rewiring itself. Every experience you have, every conversation, every book you read, every time you practice a skill or learn a new fact, the connections between your neurons change. Some connections are strengthened, others are weakened. New synapses form, old ones are pruned away. The neural network that holds your personality, your habits, your preferences, your sense of humor, your fears, all of it is in constant, quiet flux. Neuroscientists call this plasticity. Your brain is not a fixed circuit, hardwired and permanent. It is a living, breathing, changing network that reconfigures itself in response to everything you do and everything that happens to you. The you that went to bed last night is, in terms of the fine details of your neural wiring, a slightly different person from the you that woke up this morning. Sleep itself is a time of intense neural reorganization. Memories are consolidated, emotional experiences are processed, connections are reshaped. You literally sleep yourself into a slightly different brain. And this means that even the parts of you that seem permanent, even the neurons that have been with you since infancy, are not truly static. The cells persist, but the connections between them are constantly being remodeled. The hardware stays. The software is being rewritten every night. So here is a strange picture. Most of your body is constantly being replaced, piece by piece, just like the Ship of Theseus. But some critical parts, your brain cells and your heart cells, are largely original equipment. You are a ship that has had most of its planks replaced, but the keel and the mast, the core structural pieces, are still the ones you were born with.
And yet, even those core pieces are being subtly rewired. their connections reshaped, their patterns of activity altered by every experience you have. Does that make you the same you? Is the continuity of your neurons, the fact that the cells holding your memories and your personality are mostly the original ones, enough to maintain your identity? Or is even that not as reassuring as it sounds, because those neurons are themselves made of molecules and atoms that are being exchanged with the environment? Because here is the thing that makes this even more unsettling. Even your permanent cells are not made of permanent stuff. The molecules inside your neurons are being broken down and rebuilt. The proteins are being recycled. The water molecules inside each cell are being swapped out constantly. The atoms themselves, the carbon and nitrogen and oxygen that make up the proteins and the DNA, are being replaced as molecules are metabolized and new ones are synthesized. So even your brain cells, the ones that hold your memories, the ones that have been with you since before you could speak, are not made of the same atoms they were made of when you were a child. The structure has persisted. The pattern has persisted. But the physical material has been cycled through, replaced by atoms that were recently part of an apple you ate, or a glass of water you drank, or a breath of air that someone else exhaled on the other side of the world. You are a pattern that persists while the material flows through it. Like a whirlpool in a river, the whirlpool has a shape, a location, a behavior. You can point at it and say, that is a whirlpool. But the water that makes up the whirlpool is constantly changing. New water flows in, old water flows out. The whirlpool is not a thing. It is a process. It is something the river is doing. And maybe that is what you are too. Something the universe is doing.
A process, a pattern, a particular way that matter and energy are organized for a little while before they move on to be organized into something else. The ancient Greek philosophers who argued about the Ship of Theseus were asking a question about identity. What makes something the same thing over time? Is it the material, the pattern, the story we tell about it, the continuity of the process? And 24 centuries later, we still do not have a definitive answer. But we have learned something they could not have imagined. We have learned what that material actually is, down at the very bottom. We have learned what atoms are, what they are made of, and how they behave. And the answer is far stranger than anything the Greeks ever dreamed. Because when you ask what you are made of, when you go past the cells and the molecules and look at the atoms themselves, you find something that does not behave like a thing at all. For most of human history, the question of what things are made of was a matter of philosophy, not experiment. You could hold an apple, you could break it apart, you could squeeze the juice out of it, but at a certain point, the pieces were too small to see, and all you could do was think. The ancient Greeks were among the first to think about it systematically, and they came up with an idea that turned out to be surprisingly close to the truth, even though they had no way of testing it. Some of them, particularly a philosopher named Democritus, around the 5th century BC, proposed that if you kept cutting something into smaller and smaller pieces, eventually you would reach a limit. You would reach pieces so small that they could not be cut any further. He called these pieces atomos, uncuttable, indivisible, the basic building blocks of everything. Democritus imagined that atoms came in different shapes and sizes, and that the properties of different substances depended on the shapes of their atoms. Hard things were made of atoms that locked together tightly. Soft things were made of atoms that slid past each other easily. The taste of honey was caused by round, smooth atoms gliding across the tongue.
The taste of vinegar was caused by sharp, jagged atoms that pricked and stung. The variety of the world, in Democritus's vision, came from the endless ways that a finite set of atomic shapes could be combined and arranged. It was a bold piece of reasoning, considering that it was produced more than 2 millennia before anyone had the tools to observe anything smaller than a grain of sand. But it did not go unchallenged. Aristotle, the most influential philosopher in the ancient world, rejected the atomic hypothesis.
He argued that matter was continuous, that you could keep dividing it forever, and that the world was made of 4 elements: earth, water, air, and fire. For nearly 2,000 years, Aristotle's view dominated. The atoms of Democritus were largely forgotten, a footnote in the history of ideas. It was a striking idea, but it remained just an idea for more than 2,000 years. Nobody could actually see atoms. Nobody could test whether they were real or just a useful way of thinking. The atomic hypothesis sat in the margins of science, sometimes embraced, sometimes dismissed, never proven. In the early 19th century, a British chemist named John Dalton revived the idea. Dalton noticed that when chemical elements combined to form compounds, they did so in fixed, whole number ratios. Water was always made of hydrogen and oxygen in the same proportion. Carbon dioxide was always made of carbon and oxygen in the same proportion.
This made sense if matter was made of discrete, indivisible atoms. Each atom of hydrogen would combine with 1 atom of oxygen, or 2 atoms of hydrogen with 1 atom of oxygen, producing fixed ratios. Dalton's work put atoms back on the scientific agenda, but it did not prove they were real. The fixed ratios could, in principle, be explained by other theories. What was needed was direct, physical evidence of atoms. Something you could see, something you could measure, something that left no room for doubt. And then, in the early 19th century, something happened that brought atoms back into the conversation. Not through a physicist's calculations, but through a botanist's microscope. Robert Brown was a Scottish botanist born in 1773, the same year as Thomas Young, the man who would later prove that light is a wave. Brown had a distinguished career travelling the world cataloguing plants. He sailed on a ship called the Investigator, charting plant life along the coast of Australia, where he spent 3 years collecting and identifying thousands of specimens, many previously unknown to European science. He was meticulous, patient, and observant, qualities that would serve him well in making the observation that would outlast all his botanical work. His most famous observation had nothing to do with exotic flora. It happened in 1827 in London, while he was looking at something very ordinary: pollen grains floating on the surface of water. Brown put a drop of water under his microscope and watched the tiny pollen grains. He was using a microscope of reasonable but not extraordinary power, the kind available to any competent scientist of the era. And what he saw through the lens mystified him. The pollen was not sitting still. It was dancing, jiggling, trembling, moving in tiny, random, unpredictable jerks, back and forth, left and right, as though something invisible were nudging it from all sides. The motion was ceaseless. It did not slow down. It did not stop. Hour after hour, the grains kept jiggling, seemingly driven by some inexhaustible energy source. Brown watched them, fascinated, and then began the systematic investigation that characterized his best work. At first, Brown thought this might be a sign of life. Pollen comes from living plants. Maybe the grains were propelling themselves the way tiny organisms swim. But then he tried the same experiment with clearly dead material. Chalk dust, soot, ground up glass, and the jiggling was still there. Tiny particles of obviously dead, inert stuff were dancing on the surface of the water, just like the pollen. Brown could not explain it. Neither could anyone else. The dancing particles remained a mystery for nearly 80 years.
People observed it, described it, gave it a name, Brownian motion, and moved on without understanding it. The answer came in 1905, arguably the most famous year in all of science, and it came from a 26-year-old patent clerk in Bern, Switzerland, who was thinking about physics in his spare time, Albert Einstein. 1905 is usually remembered as the year Einstein published his paper on special relativity, the one that changed our understanding of space and time forever. And we will get to that, because it is central to everything we are going to talk about tonight. But Einstein actually published 4 groundbreaking papers that year, any one of which would have made him famous. And one of those papers was about Brownian motion. Einstein's insight was as simple as it was brilliant. He realized that the jiggling of the pollen grains was not the pollen propelling itself, it was being pushed.
Pushed by something invisible. Something too small to see. Something that was hitting the pollen from all sides. Imagine you are at a massive rock concert. You are deep in the crowd, pressed shoulder to shoulder with thousands of other people. The music is blasting, the crowd is restless, and every few seconds someone pushes you from the left, someone pushes you from the right, someone bumps you from behind. Most of the time, the pushes roughly cancel out, and you stay more or less in place. But sometimes, by pure chance, you get a few more pushes from one direction than from the others, and your whole body shifts a little. Then the balance shifts again, and you jiggle the other way. You are not choosing to move, you are being moved by the collective, random jostling of the crowd around you. That is exactly what Einstein said was happening to the pollen grains. The water that the pollen was floating in was not a smooth, continuous fluid.
It was made of an immense number of absolutely tiny molecules, all moving at high speed, all colliding with each other and with the pollen grain, billions of times per second. Most of the time, the collisions roughly balanced out, but every now and then, just by chance, a few more molecules would hit the pollen from one side than from the other, and the grain would lurch slightly in that direction. Then the balance would shift, and it would lurch the other way. The dancing of the pollen was the footprint of atoms. It was the visible signature of invisible molecules, the macroscopic echo of the microscopic world. Einstein did not just describe this qualitatively, he did the math. He calculated how far a pollen grain should drift on average in a given amount of time, based on the size of the water molecules, the temperature of the water, and the viscosity of the fluid. His predictions were precise and testable. If atoms were real, and if they had the properties physicists suspected, then pollen grains of a specific size in water at a specific temperature should wander a specific average distance in a specific amount of time. Within a few years, a French physicist named Jean Perrin set out to test Einstein's predictions with painstaking precision. Perrin was a meticulous experimenter, patient and methodical. He spent years preparing his experiments, developing techniques for making perfectly uniform particles of known size, and perfecting his ability to track their movements under the microscope. The work was grueling. Perrin would sit at his microscope for hours, tracking individual particles as they jiggled and wandered, marking their positions at regular intervals, logging thousands upon thousands of data points by hand. This was not the work of inspired genius having a flash of insight.
This was the work of patient, disciplined observation, repeated over and over, day after day, week after week. And the results matched Einstein's predictions beautifully. The average distance the particles wandered, the rate at which they diffused, the relationship between particle size and jiggling intensity, all of it agreed with Einstein's equations. From these measurements, Perrin was able to calculate the size of individual atoms and molecules, and his values matched estimates from other, completely independent methods. Perrin published his results in a book called Atoms in 1913, and the evidence was so overwhelming that even the last holdouts were convinced. The Austrian physicist-philosopher Ernst Mach, one of the most prominent skeptics of the atomic hypothesis, had spent years arguing that atoms were nothing more than a useful fiction. But even Mach's followers had to concede in the face of Perrin's data. In 1926, Perrin received the Nobel Prize in Physics for his work. Atoms were real. They were not just a philosophical convenience. They were physical objects, tiny beyond imagination, and they were the building blocks of everything, including you. And so, by the early 20th century, the atomic hypothesis had finally become atomic reality. The stuff you are made of, the material of your bones and blood and brain, is made of atoms. Unimaginably small atoms, so small that a single drop of water contains more atoms than there are stars in the observable universe. Trillions upon trillions upon trillions of them, packed together, bound into molecules, organized into the structures that make up your cells. That sounds satisfying in a way. You might be tempted to rest there. Okay, you are made of atoms. Atoms are small, solid building blocks. They click together like Lego bricks to build molecules, and molecules build cells, and cells build you. The material might be constantly cycling through, as we talked about earlier, but at least the fundamental pieces, the atoms themselves, are solid, definite, real objects. Little spheres of matter with a definite size and a definite location. But just as atoms were being proven to exist, physicists were already starting to crack them open. And what they found inside was not what anyone expected. Because it turned out that the uncuttable was very much cuttable, and the solid was very much empty. In 1896, just a few years before Einstein's miracle year, a French physicist named Henri Becquerel discovered something strange about uranium. He had left a sample of uranium salts sitting on top of an unexposed photographic plate in a drawer, wrapped in dark paper to keep the light out. When he developed the plate days later, he found it was fogged. The uranium had emitted some kind of invisible radiation that could pass through paper and expose photographic film without any external stimulus. This was radioactivity, and it was the first hint that atoms were not the simple, indivisible spheres that Democritus had imagined. Something was going on inside them. Something was leaking out. Marie Curie and her husband Pierre dove into this new phenomenon with ferocious intensity. Working in a converted shed at the École de Physique et de Chimie in Paris, in conditions that would horrify any modern safety inspector, they spent years processing tons of pitchblende ore, a uranium-bearing mineral, by hand. They dissolved it in acid, filtered it, precipitated it, heated it, separated it fraction by fraction, searching for the source of the mysterious radiation. The work was physically grueling. Marie Curie later described spending entire days stirring boiling masses of liquid in huge vats, her hands cracked and burned by the chemicals, her clothes and notebooks so contaminated with radioactive material that they remain dangerously radioactive to this day and are stored in lead-lined boxes at the Bibliothèque Nationale in Paris.
Visitors who wish to consult them must wear protective clothing. And yet, from this brutal labor came beauty. The Curies discovered two new elements: polonium, named after Marie's native Poland, and radium, which glowed blue in the dark with an eerie, otherworldly light. Marie Curie became the first woman to win a Nobel Prize, and the first person to win Nobel Prizes in two different sciences, physics and chemistry. She died in 1934, almost certainly from the effects of decades of exposure to the radioactive materials she had devoted her life to studying.
In 1897, while the Curies were beginning their work on radioactivity, a British physicist named J.J. Thomson discovered the electron, a tiny particle carrying a negative electric charge that could be pulled out of atoms using electric fields. Something was living inside the atom. The race to understand its internal structure was on. Thomson proposed a model. He imagined the atom as a sort of uniform blob of positive charge, with electrons embedded in it, like raisins in a cake. In Britain, they called this the plum pudding model, which is a confusing name because a plum pudding is actually a fruitcake with raisins, not plums. But the idea was clear enough. The atom was a smooth, evenly distributed mixture of positive and negative charge, and the electrons were just sitting in there, evenly spread out. It was a reasonable guess, and for a few years, it seemed like it might be right. But then a man named Ernest Rutherford decided to test it.
Rutherford was a New Zealander working in Manchester, England. He was one of the great experimental physicists, a man with a gift for designing experiments that cut straight to the heart of a question. And in the first decade of the 20th century, he set two young researchers, Hans Geiger and Ernest Marsden, to probe the structure of the atom directly. The experiment was elegant. Rutherford created a beam of alpha particles, which are tiny, fast-moving, positively charged particles emitted by radioactive materials. He aimed this beam at a thin foil of gold, just a few atoms thick, and he told Geiger and Marsden to look for what happened when the alpha particles hit the gold atoms. If Thomson's plum pudding model was correct, the alpha particles should have sailed right through the gold foil with only minor deflections. The positive charge in Thomson's atom was spread out so thinly that it would barely nudge the fast-moving alpha particles.
Maybe a few would be deflected slightly, a degree or two off their path, but nothing dramatic. So Geiger and Marsden set up their equipment. They worked in a darkened room, staring into the darkness, looking for tiny flashes of light on a fluorescent screen that would indicate where the alpha particles were landing after passing through the foil. It was tedious, painstaking work, counting flash after flash in the dark, logging each one. And most of the alpha particles did exactly what Thomson's model predicted. They sailed right through the gold foil, as though it were not there, landing on the screen more or less where they would have landed if there had been no foil at all. Some were deflected slightly, a degree here, 2 degrees there. Everything looked normal. But then Rutherford suggested something. He told Geiger and Marsden to look for alpha particles that had been deflected at large angles. Not just slightly nudged, but scattered far from the beam, maybe even bounced backward.
This was almost an afterthought. Thomson's model predicted that large-angle scattering should be essentially impossible. The diffuse positive charge in a plum pudding atom simply could not produce enough force to send an alpha particle careening off at a steep angle. It would be like firing a bullet through a cloud of dust and expecting the bullet to bounce back. But Geiger and Marsden looked. They repositioned their fluorescent screen to catch particles scattered at large angles. And they found them. Not many. Most alpha particles still went straight through. But a small fraction, about 1 in 8,000, were scattered at angles greater than 90 degrees. Some of them bounced almost straight back toward the source. Rutherford was stunned. Years later, He described the moment with a vividness that still resonates. He said it was the most incredible event of his life.
It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Think about that image for a moment. A heavy artillery shell flying at high speed, hitting something as thin and flimsy as tissue paper and bouncing back. That should not happen. The tissue paper should offer no resistance at all. And yet, that is essentially what the alpha particles were doing. Most of them passed through the gold atoms as though the atoms were empty. But occasionally, very occasionally, one of them hit something so concentrated, so dense, so impenetrable, that it was violently deflected. Rutherford spent weeks thinking about what this meant, and the conclusion he reached changed our picture of reality forever. The positive charge in the atom, he realized, could not be spread out evenly like Thompson's plum pudding. It had to be concentrated, packed into a tiny, incredibly dense point at the center of the atom.
A point so small that most alpha particles missed it entirely, sailing through the vast, empty space around it. But when an alpha particle did score a direct hit on this dense center, the electromagnetic repulsion was enormous, enough to send it flying backward. Rutherford called this dense center the nucleus, and when he calculated its size, the numbers were staggering. The nucleus was about 100,000 times smaller than the atom itself. If you scaled an atom up to the size of a football stadium, the nucleus would be a small marble sitting on the 50-yard line, and the electrons would be like gnats buzzing around in the upper decks. Everything in between, the vast majority of the atom's volume, would be empty. Nothing. Just space. This discovery did more than change our picture of the atom. It opened the door to understanding why different atoms are different, why gold is gold and lead is lead, why some elements are gases and others are metals.
And the person who walked through that door was one of the most brilliant and tragic figures in the history of science. Henry Moseley was a young English physicist, barely 25 years old, working in Rutherford's lab in Manchester. In 1913, just 2 years after Rutherford's gold foil experiment, Moseley began systematically bombarding different elements with beams of electrons and measuring the X-rays they emitted. What he found was a clean, precise pattern. The frequency of the X-rays increased in a perfectly regular way as he moved from one element to the next in the periodic table. And from this pattern, he could calculate the charge of the nucleus of each element, the number of protons. This was the key. What makes one element different from another is not its weight, as chemists had long assumed, but the number of protons in its nucleus. Hydrogen has 1, helium has 2, carbon has 6, iron has 26, gold has 79. The entire periodic table, the whole catalogue of elements that make up the material world, is organized by a single number: the number of protons in the nucleus. Moseley was 27 when he published this work. He should have had decades of brilliant physics ahead of him. But in 1915, World War I was raging, and Moseley, like many young men of his generation, volunteered for the British Army. He was sent to Gallipoli, the disastrous Allied campaign to capture the Turkish Straits. On August 10, 1915, during the Battle of Chunuk Bair, a sniper's bullet struck him in the head and killed him. He was 27 years old. Many historians of science believe that Moseley would have won the Nobel Prize had he lived. His death is often cited as one of the great losses of World War I, and it directly influenced the British government's later decision to stop sending scientists to the front lines.
One bullet, one moment, one young life ended, and the world lost a physicist who might have made discoveries we cannot even imagine. But Moseley's work survived him, and together with Rutherford's discovery of the nucleus, it gave us a clear picture of the atom, a tiny, dense, positively charged nucleus containing protons and, as was later discovered, neutrons, surrounded by a cloud of negatively charged electrons at a relatively enormous distance. And that means everything you see around you, everything you touch, everything that feels solid and real, the walls of your room, the floor beneath you, the mattress you are lying on, your own body, all of it is almost entirely empty space. The appearance of solidity is a lie, a very convincing lie, maintained by electromagnetic forces that keep the electron clouds of neighboring atoms from overlapping. When you press your hand against a table, your hand does not actually touch the table. The electron clouds in the atoms of your hand repel the electron clouds in the atoms of the table, and that repulsion feels like contact, like solidity, like touch. But in terms of actual material, there is almost nothing there. You are empty space. You have always been empty space. And the tiny fraction of you that is not empty space, the nuclei of your atoms, the electrons orbiting them, those things turned out to be far stranger still. Because the question that Rutherford's discovery immediately raised was a problem, a serious problem, one that the physics of the time could not solve. If the atom is a tiny, dense nucleus with electrons orbiting around it, like a miniature solar system, then those electrons should be doomed. James Clerk Maxwell's equations of electromagnetism, the same equations that had unified electricity and magnetism and revealed the nature of light, demanded that any charged particle moving in a curved path must radiate energy.
An orbiting electron is a charged particle moving in a curved path, so it must radiate energy. And as it loses energy, it should spiral inward, closer and closer to the nucleus, faster and faster, radiating more and more energy, until it crashes into the nucleus in a fraction of a second. According to the best physics of the day, atoms should not be able to exist. Every atom in the universe should collapse almost instantly. The matter you are made of should be impossible. And yet, here you are, here the atoms are, stubbornly, defiantly existing, refusing to collapse, refusing to obey the laws of physics as physicists understood them. Something was wrong with the laws. Something fundamental was missing from the picture. And to fix it, physicists would have to do something radical. They would have to change the rules. The year is 1900, and a 42-year-old German physicist named Max Planck is staring at a problem that will not let him sleep. Planck was not the kind of physicist who sought revolutions. He was a conservative man, methodical and cautious, deeply attached to classical physics and the elegant framework of thermodynamics that he had spent his career refining. A colleague had once advised him, when he was young, not to go into physics because the field was essentially complete. All the major discoveries had been made, the colleague said, and all that remained was to fill in the details. Planck went into physics anyway, but he shared some of that sentiment. He did not expect to overturn the foundations of the discipline. He expected to contribute careful, incremental work within the existing framework. But the problem he was working on in the autumn of 1900 refused to yield to the existing framework. And in his struggle with it, Planck would, almost against his will, strike the match that ignited the quantum revolution. The problem seems almost mundane. It is about light, specifically the light that hot objects emit. You have seen this yourself, even if you did not think about it in these terms. When you heat a piece of iron in a fire, it begins to glow. First a dull dark red, then brighter cherry red, then orange, then yellow. If you could make it hot enough, it would glow white, and then blue-white. The color of the glow depends on the temperature in a very specific, very precise way. Physicists had been trying to explain this relationship mathematically,
using the established laws of electromagnetism and thermodynamics, and they kept failing. Every calculation they tried gave the wrong answer. Worse than wrong, actually. The equations predicted that a hot object should radiate infinite energy at short wavelengths, an absurd result that they called the ultraviolet catastrophe. The math was blowing up, giving nonsensical answers, and nobody could figure out why. Planck tried everything. He combined the rules of established physics in every way he could think of, and nothing worked. And then, in what he later described as an act of desperation, he tried something that made no physical sense to him. He assumed that the energy of the vibrating atoms in the hot object could not take on just any value. He assumed that energy came in discrete chunks, in specific, indivisible packets, that he called quanta. The word comes from the Latin quantum, meaning how much. He did not believe this was actually how nature worked. He thought it was a mathematical trick, a clever device that happened to give the right answer. But the thing was, it did give the right answer. With this one strange assumption, Planck's equations perfectly matched the observed glow of hot objects. The ultraviolet catastrophe vanished. The math worked beautifully. Planck published his result in 1900 and hoped that someone, eventually, would figure out the real physics behind it.
He thought the quanta were a temporary fix, a placeholder that would be replaced by a more conventional explanation. But 5 years later, in that miraculous year of 1905, Einstein took Planck's idea and ran with it. Einstein was not just looking at the glow of hot objects. He was looking at another phenomenon, the photoelectric effect, in which light shining on a metal surface can knock electrons loose. The details of this effect were puzzling. The energy of the ejected electrons depended on the color of the light, not its brightness. Brighter light knocked out more electrons, but each individual electron came out with the same energy. Changing the color, shifting toward blue or ultraviolet, made each electron come out with more energy. Einstein realized that this made perfect sense if light itself came in discrete packets, in quanta, just as Planck had suggested. Each quantum of light, which we now call a photon, carries a specific amount of energy that depends on its frequency, its color. Blue light has higher frequency photons, so each photon packs more energy and kicks the electron harder. Red light has lower frequency photons, each carrying less energy. Brightening the light just sends more photons, but each one still carries the same individual punch. This was a startling claim. For more than a century since Thomas Young's double-slit experiment in the early 1800s, physicists had known that light behaves as a wave. Waves of electromagnetic energy rippling through space, showing all the hallmark behaviors of waves: interference, diffraction, the ability to bend around corners and combine to form patterns. Young had demonstrated this conclusively. Maxwell had built it into his equations. Light is a wave. That was settled science. And now Einstein was saying that light also comes in particles. Discrete, countable, individual packets of energy. Not sometimes a wave and sometimes a particle depending on the experiment, but somehow both at once, in a way that defied easy visualization. This was the first glimpse of what would become the central mystery of quantum mechanics: wave-particle duality. And it was about to get much stranger, because it was not just light that behaved this way. Matter did too. In 1924, a French aristocrat and physicist named Louis de Broglie was watching the quantum revolution unfold and thinking about symmetry. De Broglie came from one of the oldest noble families in France, a family that had produced politicians, diplomats, and military officers for centuries. His older brother, Maurice, was already an accomplished experimental physicist. Louis himself had originally studied history before turning to physics,
and he brought to the subject a taste for bold, sweeping ideas. His boldest idea was simple and striking.
If light, which everyone had thought was a wave, could also behave like a particle, Einstein's photon, then why not the reverse? Why could particles, things like electrons, which everyone thought of as tiny solid objects, not also behave like waves? Nature, de Broglie felt, should be symmetric. If waves can be particles, particles should be waves. De Broglie proposed exactly that in his doctoral thesis, one of the most consequential PhD dissertations ever written. He declared that every particle of matter has a wavelength associated with it, a wavelength that depends on the particle's momentum. The faster and heavier the particle, the shorter the wavelength. For objects in everyday life, baseballs, cars, people, the wavelength is so incomprehensibly tiny that it has no observable effect. You have a wavelength right now, lying here, but it is roughly 10 to the power of -35 meters. So unimaginably small that it is a trillion times smaller than the nucleus of an atom. The wave nature of your body is utterly invisible. But for something as small and light as an electron, the wavelength is significant. It is comparable to the size of an atom. And if electrons have wavelengths, they should show wave behavior. They should be able to interfere with each other, just like light waves do in Young's double-slit experiment. De Broglie's thesis examiners were not sure what to make of it. The idea was so radical that they sent the thesis to Einstein for a second opinion. Einstein read it and replied that de Broglie had lifted a corner of a great veil. The thesis was accepted, and de Broglie received his doctorate. When this idea was first proposed, it sounded bizarre. Electrons as waves? Particles of matter rippling through space like water waves? But within a few years, experiments confirmed it. Beams of electrons were fired at crystalline targets, and the patterns they produced on detectors showed the unmistakable signature of wave interference. Places where the electron waves added together and strengthened, producing bright spots. Places where they cancelled each other out, producing dark spots. The regular rhythmic pattern of waves combining, the electrons were not just particles, they were also waves, both at once. And then, in 1926, a physicist named Max Born provided the interpretation that still sits at the heart of quantum mechanics today. An interpretation that is as unsettling as it is successful. Born said that the wave associated with a particle, the quantum wave, is not a wave of anything physical. It is not a wave of matter or energy rippling through space. It is a wave of probability. Think about what that means. When an electron is traveling from one place to another, it does not follow a definite path. Instead, its probability wave spreads out, rippling through space, existing in many places at once, like a ripple on a pond that extends in all directions. The wave tells you the chances of finding the electron here or there, in this place or that place. Where the wave is strong, the electron is more likely to be found. Where the wave is weak, it is less likely. But until something interacts with the electron, until something measures it or detects it, the electron does not have a definite location. It is, in a very real sense, everywhere its wave reaches, all at once. And then, when a detector clicks, when something does interact with the electron, the wave collapses. The probability wave, which had been spread out over a wide area, suddenly snaps to a single point, and the electron appears, definitively, at one specific location. The spread out, everywhere at once wave becomes a localized, here and now particle. This is strange enough for a single electron. But you are made of electrons. You are made of trillions of trillions of trillions of them. And each one of them, when it is not being observed in the quantum sense, when it is not interacting with something that pins it down, exists as a probability wave spread out over space. To really see this in action, to appreciate just how deeply strange it is, consider the double-slit experiment, which many physicists consider the most beautiful and the most disturbing experiment in the history of science. Imagine a barrier with two narrow slits in it, and behind the barrier, a screen that can detect where particles land. If you fire tiny bullets at the barrier, classical bullets, some go through the left slit, some go through the right slit, and they pile up on the screen in two clusters, one behind each slit. That is what you would expect from particles. Now fire a beam of electrons at the same barrier. You might expect the same thing, two clusters, one behind each slit. But that is not what happens. Instead, the screen shows an interference pattern, a series of bright bands and dark bands spread across the screen, exactly like the pattern you get when you send waves through two slits. The electron waves coming through the two slits overlap and interfere with each other, adding together in some places and cancelling in others, producing the characteristic striped pattern. Okay, so electrons are waves, fine. But here is where it gets truly strange. Reduce the intensity of the electron source so that only one electron at a time goes through the apparatus. One single electron alone approaching the barrier. It goes through which slit? You might think it has to go through one or the other. It is, after all, one electron. It is a single particle. It cannot go through both slits at once. Can it? You fire the electrons one at a time. Each one lands on the screen at a single point, a definite dot. That is particle behavior. But if you let enough individual electrons accumulate on the screen, one after another, over the course of hours, the dots build up into a pattern. And the pattern is the interference pattern. The same striped, wave-like pattern that you get from sending a continuous beam through both slits. Each individual electron somehow went through both slits at once. Each one interfered with itself. Each one was a wave spread out across both paths, and when it hit the screen, it collapsed into a single point. But the probability of where that point landed was governed by the interference of the wave that passed through both slits simultaneously. Now here is the final twist, the part that made Einstein uncomfortable for the rest of his life. If you put a detector at one of the slits, a device that tells you which slit the electron went through, the interference pattern disappears. The electrons start behaving like classical particles, going through one slit or the other, and the pattern on the screen becomes two simple clusters, one behind each slit. No interference, no wave behavior. The act of observing which slit the electron goes through changes how the electron behaves. When you are not looking, when you are not measuring which path it takes, the electron behaves like a wave, passing through both slits simultaneously. When you do look, when you do measure, it behaves like a particle, passing through one slit. This is not a failure of the equipment. It is not a problem of measurement disturbing the electron. It is deeper than that. The quantum world genuinely behaves differently depending on whether information about the particle's path is available. The wave-like or particle-like behavior is not a property of the electron alone. It is a property of the entire experimental setup, including the presence or absence of a detector. The mathematical framework that describes these probability waves was developed by an Austrian physicist named Erwin Schrödinger in 1926. He wrote an equation, the Schrödinger equation, that describes how the quantum wave of a particle evolves over time. It is the quantum analog of Newton's laws of motion. Just as Newton's equations tell you where a cannonball will be at any future moment, Schrödinger's equation tells you how the probability wave of a quantum particle will spread and change as time passes. And the equation is clean and spare. It is clean, elegant, and deterministic. Given the wave function at one moment, the Schrödinger equation predicts it perfectly at every future moment. There is no randomness in the equation itself. The randomness only enters when you measure the particle, when you force the spread-out wave to collapse into a definite outcome. The evolution of the wave is perfectly predictable. The result of the collapse is not. This tension between the deterministic wave and the random collapse troubled many physicists, and it still does. What happens during the collapse? Why does the smooth, deterministic evolution of the wave function suddenly give way to a random jump? What counts as a measurement? Does a photon detector count? Does a bacterium count? Does a cat count? Schrödinger himself highlighted the absurdity of the collapse with a thought experiment that has become one of the most famous images in all of science. Imagine a cat in a sealed box, he said. Inside the box there is a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter clicks, triggers a mechanism, breaks the vial, and the cat dies. If the atom does not decay, the cat lives. Now, the atom is a quantum object. Before anyone checks, it is in a superposition of decayed and not decayed. According to quantum mechanics, until a measurement is made, the atom has not committed to either state.
And if the cat's fate is linked to the atom's state, then the cat too is in a superposition of alive and dead. Not one or the other, both at the same time. Schrödinger did not propose this thought experiment because he believed the cat was really both alive and dead. He proposed it to show that the quantum rules, if taken literally, lead to absurd consequences when applied to everyday objects. The cat is alive or dead, obviously. Something must happen at some point to force reality to choose. But the equations do not tell us where that line is. The equations are silent about where the quantum world ends and the classical world begins. This is the measurement problem. It is one of the deepest unsolved problems in quantum mechanics. And after nearly a century of debate, there is still no consensus on the answer. Different physicists have proposed different solutions. The Copenhagen interpretation, associated with Niels Bohr, says that the wave function is not a physical thing. It is a tool for calculating probabilities, and asking what happens between measurements is meaningless. The question simply has no answer. Reality, in Bohr's view, only exists when it is observed. Hugh Everett proposed the many worlds interpretation, in which the wave function never collapses at all. Instead, every quantum measurement causes the universe to split into branches, one branch for each possible outcome. In one branch, the cat is alive. In another, the cat is dead. Both branches are equally real, but they can never communicate with each other. You, right now, are just one version of yourself in an unimaginably vast tree of branching realities, each one as real as the next. David Bohm proposed a pilot wave interpretation, in which particles really do have definite positions at all times, guided by a quantum wave that tells them where to go. In Bohm's picture, there is no randomness at all. Everything is deterministic. The apparent randomness of quantum mechanics is an illusion created by our ignorance of the initial conditions. Each of these interpretations makes exactly the same predictions for every experiment that has ever been performed. They are empirically indistinguishable. The choice between them is, at least for now, a matter of philosophical taste rather than experimental evidence. The equations work the same way regardless of which story you tell about what they mean. And this ambiguity, this inability to choose between radically different pictures of reality, even after a century of effort, tells you something about the depth of the quantum mystery. The universe, at its deepest level, refuses to be pinned down. Born received his Nobel Prize in 1954 for his probability interpretation. By that time, it had been tested in countless experiments and had never failed. Quantum mechanics, with its probability waves and its collapse upon measurement, is the most accurate scientific theory ever devised. Its predictions match experiment to a staggering number of decimal places. But Einstein never accepted it.
He spent the last decades of his life arguing that quantum mechanics could not be the complete picture. He was not arguing that the math was wrong. The math clearly worked. He was arguing that there must be something deeper beneath the probabilities, some hidden variables, some underlying deterministic reality that quantum mechanics was merely approximating. In a letter to Born, his friend and intellectual sparring partner, Einstein wrote a line that has become one of the most famous sentences in the history of physics. "I, at any rate, am convinced that God does not throw dice." Born disagreed. Most physicists disagreed. And eventually, as we will see, experiments were devised that tested whether Einstein's hidden variables could exist.
The results were conclusive, and they pointed to a reality even stranger than Einstein had feared. But that comes later. For now, just sit with this for a moment. You are made of atoms. Those atoms are mostly empty space, and the tiny pieces inside them, the electrons and quarks and other fundamental particles, are not solid objects sitting in definite locations. They are probability waves, spread out, undefined, existing in a blur of possibilities until something interacts with them and forces them to become definite. The matter you are made of is, at its deepest level, not quite matter at all. It is a shimmering cloud of maybes, a fog of probability, a wave of potential that only becomes something concrete when it is measured, when it interacts, when it participates in the ongoing conversation between particles and forces that we call reality. You are made of this. Your thoughts are encoded in the electrical activity of neurons made of this.
Your memories are stored in the synaptic connections between cells made of this. The warmth you feel, the weight of the blanket, the sound of these words, all of it is, at the deepest level, probability waves collapsing into definite experiences. And if that is unsettling, if it makes the ground feel a little less solid beneath you, hold on. Because there is something else going on in the quantum world, something that Einstein himself found so disturbing that he spent the last decades of his life fighting against it. Something that connects the particles in your body to particles on the other side of the universe in a way that defies every intuition you have about how separate things should behave. We are not quite done with the quantum world. There is one more piece of this puzzle that we need to pick up before we move on. Because it changes everything about how we think about reality, about what it means for something to exist, and about whether the universe is really out there, independent of you, or whether your observation of it plays a deeper role than anyone ever imagined. It starts with a thought experiment that Einstein came up with in 1935, together with two colleagues, Boris Podolsky and Nathan Rosen. Einstein was still bothered by quantum mechanics. He accepted that the math worked, but he could not accept that the universe, at its deepest level, was genuinely random, genuinely probabilistic, genuinely undetermined until someone looked. He believed that there had to be hidden variables, some deeper layer of reality beneath the quantum probabilities, something definite and deterministic that we simply had not found yet. So he designed a thought experiment to show that quantum mechanics must be incomplete. It is called the EPR paradox, after the initials of the three authors, and it goes like this. Imagine that you create two particles in a single event, some kind of interaction that produces a pair. These two particles are linked, entangled, because they were born together. One of the things that links them is a property called spin. You can think of spin, very loosely, as the particle rotating in one direction or another, though in quantum mechanics, spin is much stranger than actual rotation. What matters is that the two particles are created so that their spins are opposite. If one is spinning up, the other must be spinning down, because the total spin has to add up to zero, which is what it was before the pair was created. Spin is conserved. Now here is where quantum mechanics says something strange. Before you measure the spin of either particle, neither particle has a definite spin.
Each one exists in a superposition, a blur of both possibilities, 50% chance of up and 50% chance of down. The spin is not determined until someone measures it. Let the two particles fly apart. Let them travel in opposite directions for as long as you like. Light years apart if you want. They are still entangled, still linked by their shared quantum state. Now measure the spin of one of them. Your detector beeps and reads spin up. Instantly, you know that the other particle, the one that might be light years away, must be spin down. The wave function has collapsed. The probabilities have resolved. Both particles now have definite spins. But think about what just happened. Before your measurement, neither particle had a definite spin. Both were in a blur of up and down. And then, the instant you measured one of them, the other one, far away, snapped into a definite state too. Instantly. Not at the speed of light, instantly. Einstein was horrified by this. In a letter to Max Born, he called it "spookhafte Fernwirkungen," spooky action at a distance. He argued that this could not be real. It violated everything he believed about the universe. Nothing can travel faster than light, and certainly not information or influence. The only sensible explanation, Einstein said, was that the particles had definite spins all along. The spins were determined at the moment of creation, and quantum mechanics simply did not know about them. The particles were carrying hidden information, hidden variables, like sealed envelopes with the answers already inside. When you opened one envelope, you learned what was in the other, but nothing had traveled between them. The information was there all along. This seemed like a perfectly reasonable argument, and for nearly 30 years, it was just a philosophical debate. Einstein and Bohr argued about it endlessly, and there seemed to be no way to settle the question experimentally. Hidden variables or genuine quantum weirdness? How could you possibly tell the difference? And then, in the early 1960s, a quiet, brilliant Irish physicist named John Stuart Bell figured out how. Bell was born in Belfast in 1928. He had decided early in life that he wanted to be a scientist, and by 1960, he was working as a theoretical physicist at CERN, the European Organization for Nuclear Research, on the French-Swiss border. Bell was deeply interested in the foundations of quantum mechanics, which was unusual for a physicist of his generation. Most physicists had adopted a pragmatic attitude. The equations work. Do not worry about what they mean, just shut up and calculate. But Bell could not stop worrying about what they meant. And in 1964, he published a theorem that changed the conversation forever. Bell's insight was subtle but devastating. He showed that if Einstein was right, if the particles really did carry hidden variables that determined their properties all along, then the results of certain experiments would have to obey specific mathematical limits. These limits are called Bell inequalities. They set boundaries on how strongly correlated the measurements of two entangled particles can be, if the correlations are explained by pre-existing hidden information. But if quantum mechanics was right, if the particles genuinely did not have definite properties until measured, and if measuring one really did instantaneously affect the other, then the correlations would be stronger. They would violate the Bell inequalities. They would exceed the limits that hidden variables could produce. In other words, Bell found a way to distinguish between Einstein's view and the quantum view. Not philosophically, but experimentally. You could actually do the experiment and see which prediction was correct. The race to test Bell's theorem began almost immediately. It was not easy. The experiments required exquisitely precise measurements of entangled particles, with detectors aligned at specific angles to catch subtle differences in the correlations. Early experiments were suggestive but not conclusive. There were loopholes, ways that hidden variables could potentially sneak in and mimic the quantum predictions. But over the decades,
the experiments got better and better. In the 1980s, the French physicist Alain Aspect conducted a series of landmark experiments that closed several important loopholes. He used rapidly switching detectors that changed their measurement settings while the entangled photons were still in flight, so that no signal, not even one traveling at the speed of light, could carry information between the detectors in time to affect the results. The correlations exceeded Bell's limits. Hidden variables were ruled out. Reality was non-local.
Measuring one particle really did affect the other, instantly, across whatever distance separated them. Over the following decades, experiment after experiment confirmed this. The loopholes were closed one by one. In 2015, a Dutch group at Delft University conducted what many consider the definitive test, closing all major loopholes simultaneously. The results were unambiguous. And then came an experiment so extreme that it borders on the poetic: the cosmic Bell test. The worry with any Bell experiment is that the equipment, the detectors, the photon sources, even the experimenters themselves, are all made of atoms. Atoms that have been around for billions of years. Atoms that have had countless opportunities to interact with each other over the history of the universe. What if, over all those billions of years, some subtle correlations had built up between the atoms in the equipment and the atoms in the particles being tested?
What if the hidden variables were not carried by the individual particles, but were somehow imprinted in the shared history of all the matter involved in the experiment? To close this loophole, physicists decided to set the measurement settings of their detectors using something that could not have been influenced by the particles being tested. They used the light of distant stars, fluctuations in the starlight, random flickerings that had been traveling through space for hundreds of years, were used to determine the angles at which the detectors measured the spins of the entangled particles. The idea was that these stellar fluctuations were set in motion long before the experiment existed, long before the equipment was built, long before the experimenters were born. No hidden variable could have anticipated them. And again, the results violated Bell's inequalities. Reality is non-local.
The experiment was even repeated using the light of distant quasars, pushing the origin of the measurement settings back almost 8 billion years, to a time when the universe was less than half its current age. And still, the correlations exceeded Bell's limits. Reality is genuinely, experimentally, conclusively non-local. What does this mean? It means that the universe is not a collection of separate objects sitting in definite states, independent of each other. Particles that have interacted are linked, entangled, sharing a quantum state that extends across space. Measuring one of them does not merely reveal a pre-existing property. It determines a property, and that determination affects the partner, wherever it is, instantly. An electron is not simply an electron. It is entangled with other particles, sharing quantum states that span distances that can stretch across a laboratory, across a country, across the solar system, across the galaxy. Nothing in the universe is truly isolated. Everything is connected through a web of quantum correlations that we are only beginning to understand. And the strangeness goes deeper still. John Wheeler, one of the most creative physicists of the 20th century, proposed a thought experiment called the delayed choice experiment that pushes the implications of quantum mechanics to their most disturbing extreme. Remember the double slit experiment? When you do not look at which slit the electron goes through, it goes through both and produces an interference pattern. When you do look, it goes through one and the pattern disappears. Wheeler asked, what if you wait until after the electron has already passed through the slits before you decide whether to look? He imagined a cosmic version of this experiment,
Light from a distant quasar passes through the gravitational field of a galaxy between the quasar and Earth. The galaxy acts like a gravitational lens, bending the light around it, creating two possible paths, like two slits in a cosmic barrier. The light left the quasar billions of years ago. When the light finally arrives at Earth, you can choose how to detect it. If you set up your detector to determine which path the photon took, left or right around the galaxy, the photon behaves like a particle that took one path. If you set up your detector to look for interference, the photon behaves like a wave that took both paths simultaneously. Here is the disturbing part. Your choice of detector, made now, today, in your laboratory, seems to determine how the photon behaved billions of years ago when it passed the galaxy. Did it take one path or both? The answer depends on a measurement you have not made yet. Wheeler's delayed choice experiment has been performed in laboratories, not with quasars but with mirrors and beam splitters, and the results confirm the prediction. The experimenter's choice of measurement, made after the photon has already passed the point of decision, determines whether the photon traveled as a particle or a wave. The present seems to influence the past. This does not mean you can send messages to the past or change history. No information is transmitted faster than light. The correlations only become visible when you compare the results of the two detectors after the fact. But it does mean that the quantum world refuses to commit to a definite history until that history is recorded, observed, made part of the permanent record. The past, in some deep quantum sense, is not fully real until it is observed. You might be sharing Einstein's feeling right now, that this is a step too far, that there is no way the atoms in your body are entangled with particles on the other side of the galaxy. But the universe does not care about your feelings. It does not care about your intuition. It refuses to behave in a way that feels sensible to a brain that evolved to track predators on the African savanna and find ripe fruit in the trees. The 2022 Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their decades of experiments on entangled particles. The Nobel Committee's citation was direct. They had demonstrated that the universe violates Bell inequalities. Reality, at its deepest level, is not a collection of independently existing things with predetermined properties. It is something stranger, something more interconnected, something that refuses to fit neatly into the boxes our minds want to put it in.
And so here you are, lying in the dark, made of atoms that are mostly empty space, held together by electromagnetic forces that are ultimately described by probability waves. In a universe where the deepest pieces of reality are entangled with each other across cosmic distances and do not have definite properties until they are measured. What then are you? Let's set that question aside for now. Not because we are done with it, but because there is another layer to this story, a layer that changes the question itself. We have been talking about what you are made of, and the answer has gotten progressively stranger with each step. But we have been assuming this whole time that at least one thing is solid and reliable: the flow of time. The steady progression of seconds, one after another, carrying you from the past into the future. The clock on your wall, the beating of your heart.
The sense that right now is right now, and a moment ago is gone, and a moment from now has not yet arrived. What if that is not solid either? What if time, the very fabric of your existence, the medium through which you experience being alive, is not the simple, universal, evenly flowing thing you think it is? To answer that, we have to go back. Back before quantum mechanics, back before the atom was split, back to the time when the rules of physics seemed clear and complete and beautiful. And one man looked at those rules and found a crack that would shatter the whole picture. Before Einstein, time was simple, not easy exactly. Newton's mechanics could be fiendishly complicated to apply. Predicting the orbits of three gravitating bodies was a problem so difficult that it occupied mathematicians for centuries. But the underlying idea of time was simple. Time was a backdrop, a stage, an invisible river flowing at a constant rate, everywhere in the universe, regardless of what was happening in it. 1 second in London was the same as 1 second on the moon, was the same as 1 second on a star a billion light years away. Time ticked, uniformly, universally, for everyone and everything, and nothing you could do would change that. This idea of absolute time was baked into the foundations of Newtonian physics. It was not just an assumption, it was a necessity. Newton's laws of motion, the laws that describe how objects move when forces act on them, require a universal clock. They require that everyone, everywhere, agree on what "at the same time" means. Without that agreement, the laws do not work. The whole mathematical structure collapses. But to understand how we got to Newton's absolute time and why it seemed so natural for so long, we need to go back a little further. To a sickbed, a fly, and a corner of a ceiling. In November of 1619, a young French mercenary named René Descartes was fighting for the Dutch Protestant state. The weather was bitterly cold, and Descartes shut himself away in a small, heated room to avoid the chill. He was ill, confined to his bed, staring aimlessly at the ceiling, and he noticed a fly. The fly was walking across the ceiling, pausing, then launching into flight, darting about the room, landing on a wall, then returning to the ceiling. Descartes watched it idly, and a thought wandered across his mind. How could he describe the fly's position? How could he pin down mathematically exactly where the fly was at any given moment? He realized that he needed a reference point. He chose the corner of the room, the point where two walls meet the ceiling. From that corner, he imagined 3 lines running along the edges, 1 along each join. 3 axes meeting at right angles. And at any instant, the fly's position could be described by 3 numbers, its distance along each of these axes. 3 numbers. That is all you need to specify a location in 3-dimensional space. This seems obvious to us now. We teach it to children. Every point on a map, every location in a GPS, every pixel on a screen is specified by coordinates. But in 1619, it was a revelation. Descartes had invented the coordinate system, the mathematical framework that allows us to describe position and motion with numbers. His name is still attached to it, Cartesian coordinates. Descartes died in 1650, unaware that a boy growing up in the English countryside would take his coordinate system and build the foundations of modern physics on top of it. Isaac Newton was born in 1642, on Christmas Day, in the tiny village of Woolsthorpe in Lincolnshire. He was a strange, solitary child, given to building mechanical models and staring at the sky. By his early 20s, he was already one of the most brilliant mathematicians in England and possibly the world. In 1666, when Newton was 23, the bubonic plague returned to England. It was not the first time. The Black Death had been recurring in Europe for centuries, each wave killing tens of thousands. The universities closed. Students and faculty fled to the countryside. Newton left Cambridge for his family farm in Woolsthorpe and spent the next 2 years largely alone, thinking. It was during this enforced solitude, this retreat from civilization, that Newton made many of his greatest breakthroughs. In just 2 years, alone on a farm in the English countryside, with the plague keeping everyone indoors and the world grinding to a halt, Newton produced a body of work that would have been an astonishing achievement for an entire generation of scientists. He passed a beam of sunlight through a glass prism and watched it fan out into a rainbow, red through violet, proving that white light is a mixture of all colors. He invented calculus, the mathematical language of change, the tool that allows you to describe how things grow and shrink and accelerate and decelerate. the tool that would become the foundation of virtually all of physics and engineering. And he formulated his laws of motion, the 3 rules that describe how objects move when forces act on them. Newton later described this period with characteristic understatement. "In those days I was in the prime of my age for invention," he wrote, "and minded mathematics and philosophy more than at any time since." Philosophy, in Newton's era, meant what we now call science, and the philosophy Newton was minding would reshape human understanding of the universe.
There is a legend, probably apocryphal, that Newton was sitting under an apple tree in the garden at Woolsthorpe when an apple fell on his head, inspiring his theory of gravity. The real story is likely more mundane. Newton saw an apple fall, or perhaps many apples on many occasions, and he wondered about the force that pulled the apple toward the Earth. Was it the same force that held the moon in its orbit? Was it the same force that kept the planets circling the sun? Could all of these motions be explained by a single law? They could. Newton's law of universal gravitation said that every mass in the universe attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. One law, one equation. And it explained the orbits of the planets, the trajectory of a thrown ball, the rhythm of the tides, the paths of comets, the motion of the moon.
Everything fell into place, literally, under the pull of one universal force. Newton's laws needed a stage. They needed a background of space and time against which motion could be defined. And Newton provided one. Space, he said, is absolute. It extends infinitely in all directions, a fixed, unchanging grid. And time is absolute too. It flows at a constant rate, everywhere, uniformly, a single cosmic clock ticking away in the background. In Newton's universe, time is a true absolute, a single clock that ticks across the entire cosmos, a tick that everyone agrees on. Space was slightly more complicated, because Galileo had already shown that motion is relative. If you are on a ship sailing smoothly on a glassy sea, there is no experiment you can do below deck that will tell you whether the ship is moving or sitting still in the harbor. The physics is the same either way. Every observer has the freedom to define the origin of their own coordinate system, and the laws of motion are the same for all of them, as long as they are not accelerating. Galileo had thought about this deeply, and he wrote about it with a vividness that still makes physicists smile. In his great work, The Dialogue Concerning the Two Chief World Systems, published in 1632, he described an elaborate thought experiment. Imagine being below deck on a large ship, he said. Shut yourself in the main cabin. Bring with you some small flying animals, butterflies or gnats. Have a large bowl of water with some fish in it. Hang up a bottle that drips water into a wide vessel beneath it. Now have the ship move at any speed you like, as long as the motion is uniform and not fluctuating this way and that. You will discover not the least change in any of the effects described. The butterflies will flutter about with equal ease in every direction.
The fish will swim toward any side of the bowl, without preferring one direction over another. The drops will fall from the bottle into the vessel below without deviating. You could jump just as far forward as backward. If you toss something to your companion, you will need to throw it with equal force in every direction. And here is the key observation. You could not, from any of these effects, determine whether the ship was moving or standing still. No experiment performed below deck could reveal the ship's motion. Only if the ship lurched, if it accelerated or decelerated or turned, would the fish drift to one side of the bowl, the butterflies struggle, the drops miss the vessel. Galileo was making a critical point, one that would echo through the centuries and become one of the cornerstones of modern physics. Uniform motion is undetectable from within. Only changes in motion, accelerations, can be felt.
If you are moving at a constant speed in a straight line, you might as well be standing still. The physics is identical. This was the first theory of relativity, Galilean relativity, the principle that the laws of motion are the same for all observers in uniform motion. No experiment can detect absolute motion. Only relative motion matters. It is worth pausing to appreciate how radical this idea was when Galileo first proposed it. For most of human history, people believed in an absolute state of rest. The Earth was still, and everything else moved around it. The sun rose and set. The stars wheeled overhead. Motion was something that happened against the fixed backdrop of a stationary world. To say that motion was relative, that there was no experiment that could distinguish between moving and not moving, was to undermine the entire intuitive framework through which people understood their place in the universe. And yet, Galileo was right. He knew it not through abstract reasoning alone, but through careful observation and brilliant thought experiments. And his insight would become one of the most durable principles in all of physics, surviving every revolution that followed, from Newton through Einstein and beyond. Newton built this into his equations. Every observer in uniform motion can use Newton's 3 laws to calculate the outcomes of experiments, and they will all get the same answers. The laws of physics are the same on a moving train as on the platform. You can drop a ball on the platform and watch it fall straight down. You can drop a ball on a smoothly moving train and it falls straight down just the same. The physics does not care about your constant velocity, it only cares about acceleration. This was a powerful, internally consistent picture of the universe, and it worked spectacularly well. Newton's laws predicted the motions of planets, the trajectories of cannonballs, the behavior of tides, the orbits of moons. For more than 2 centuries, Newtonian mechanics was the gold standard of physics, the most successful scientific theory ever created. And throughout all of those centuries, nobody seriously questioned the idea of absolute time. It felt right. It matched experience. Clocks everywhere seemed to agree. Seconds seemed to be the same length no matter where you were or how fast you were going. Time flowed, steady and universal, a silent river carrying everything along at the same pace. But there was a crack in this beautiful picture, and the crack had to do with light. In the middle of the 19th century, a Scottish physicist named James Clerk Maxwell achieved something remarkable, something that Einstein himself later called the deepest and most fruitful contribution to physics since Newton. Maxwell was born in Edinburgh in 1831 and grew up on his family's estate in the Scottish countryside. He was a quiet, curious child who constantly asked questions. When adults gave him an answer, he would reply with a question that has since become famous in the annals of scientific biography. But what is the particular go of that? He wanted to understand the mechanism, the underlying reason, the way things actually worked beneath the surface. Maxwell's achievement was to take 2 phenomena that had seemed completely separate, electricity and magnetism, and show that they were 2 aspects of a single thing, the electromagnetic field. The experimental hints had been accumulating for decades. In 1820, the Danish physicist Hans Christian Ørsted noticed that a current-carrying wire deflected a nearby compass needle. Electricity was creating magnetism. In 1831, Michael Faraday, the self-taught genius who had started his career as a bookbinder's apprentice, discovered the reverse. A changing magnetic field could induce an electric current in a wire. Magnetism was creating electricity,
The two forces were intertwined, feeding into each other, but nobody could explain exactly how. Faraday did not have the mathematical training to express his insights in equations. He thought in terms of physical pictures, imagining lines of force radiating out from magnets and charges, filling space with invisible patterns of influence. These lines of force were Faraday's great contribution, a way of visualizing fields that is still used in physics classrooms today. Maxwell took Faraday's physical intuition and translated it into mathematics. He wrote down a handful of equations, 4 in their modern form, that described every known electrical and magnetic phenomenon in a unified framework. Every experiment, every observation, every interaction between charges and currents and magnets, all of it was captured in Maxwell's equations. This was already an immense achievement. Maxwell had unified two of nature's fundamental forces into a single framework. But when he looked deeper into his equations, when he manipulated them and combined them and explored their mathematical structure, he found something unexpected and deeply strange. His equations implied that disturbances in the electromagnetic field would propagate through space as waves. Oscillating, intertwined fields of electricity and magnetism, leapfrogging each other into the void. And when he calculated the speed at which these waves would travel, the number came out to be about 300,000 kilometers per second. That was the speed of light. Light was electromagnetic waves.
The light you see by, the warmth you feel from the sun, the radio signals that carry music to your speakers, the X-rays that photograph your bones. All of it was vibrations in the electromagnetic field, differing only in wavelength and frequency. Maxwell had not just unified electricity and magnetism, he had explained light. But there was a problem. Maxwell's equations gave a definite speed for light: 300,000 kilometers per second. The equations did not specify what this speed was relative to. In Newtonian physics, every speed is relative. A train moves at 100 kilometers per hour relative to the ground. But relative to a passenger sitting inside, it is not moving at all. Speeds depend on your frame of reference. So when Maxwell's equations said the speed of light was 300,000 kilometers per second, the natural question was, relative to what? What was the reference frame in which light had exactly that speed?
Many physicists assumed the answer was the ether. This was a hypothetical substance, invisible and weightless, that was supposed to fill all of space. Light, in this picture, was a wave in the ether, just as sound is a wave in air. The ether was the medium through which light propagated, and the speed of light was its speed relative to the ether. If the ether existed, then it defined an absolute rest frame for the universe. You could, in principle, measure your speed relative to the ether by looking at how fast light travels in different directions. If you were moving through the ether, light should travel slightly faster toward you and slightly slower away from you, just as sound seems to change pitch when a fire engine passes by. In 1887, two American physicists, Albert Michelson and Edward Morley, built an exquisitely sensitive instrument to detect exactly this effect. Their interferometer split a beam of light into two paths at right angles, sent each beam along its path and back again, and then recombined them. If the Earth was moving through the ether, the two beams would travel slightly different distances relative to the ether, and when they recombined, they would be slightly out of step. This would produce a measurable interference pattern, a set of bright and dark bands that would shift as the apparatus was rotated. Michelson and Morley expected to see a shift, Everyone expected to see a shift. It was supposed to be a straightforward measurement of the Earth's speed through the ether. Michelson had in fact already tried this experiment once before, in 1881, using a less sensitive apparatus, and had gotten inconclusive results. The 1887 version was designed to be definitive.
They mounted their interferometer on a massive sandstone slab, which floated in a trough of liquid mercury to eliminate vibrations and allow the apparatus to be rotated smoothly. The mercury acted as a frictionless bearing, so that the entire instrument could be turned to different orientations while the light beams continued their journeys undisturbed. The sandstone slab weighed about 1.5 tons. The mercury trough was in the basement of a stone building. Every precaution was taken to eliminate stray vibrations, temperature fluctuations, and other sources of error. They ran the experiment in July 1887, taking measurements at different times of day and at different orientations of the apparatus. They repeated the measurements again and again, looking for the telltale shift in the interference pattern that would reveal the Earth's motion through the ether. They saw nothing. No shift, no difference. No matter how they oriented their apparatus, no matter what time of day, the speed of light was the same in every direction. The ether wind did not exist. This was baffling. The Michelson-Morley experiment is sometimes called the most famous failed experiment in the history of science. It found nothing, and that nothing changed everything. For nearly 2 decades, physicists struggled with this result. Various explanations were proposed. Maybe the ether was dragged along by the Earth. Maybe objects moving through the ether were physically compressed in the direction of motion, just enough to cancel the expected effect. These ideas were clever, but they felt like patches, ugly fixes added to save a theory that was starting to look flawed. And then, in 1905, the 26-year-old patent clerk in Bern cut through the entire mess with 2 simple statements that demolished the physics of the previous 3 centuries. Einstein's approach was radical in its simplicity. He did not try to explain why the Michelson-Morley experiment found nothing. He did not try to save the ether. He did not add patches or complications. Instead, he started from scratch, with just 2 principles, and followed them wherever they led. The first principle was Galileo's. The laws of physics are the same for all observers in uniform motion. This was not controversial. Newton had built his entire mechanics on it. Einstein simply extended it. He said that all the laws of physics, not just mechanics but also electromagnetism, must be the same for all observers in uniform motion. No experiment of any kind, mechanical or electromagnetic, can detect absolute motion. The second principle was the one that shattered everything. Einstein said that the speed of light is the same for all observers, not just relative to the ether, not just in some special reference frame, for everyone, regardless of how fast they are moving. Think about how strange that is. If you are standing on a train platform and a ball is thrown forward at 30 kilometers per hour from a train that is moving at 100 kilometers per hour, you see the ball moving at 130 kilometers per hour. Speeds add up. That is everyday experience. But Einstein said that if you are standing on a platform and a beam of light is shone forward from a train moving at 200,000 kilometers per second, you do not see the light moving at 500,000 kilometers per second. You see it moving at 300,000 kilometers per second. Exactly the same speed you would see if the train were standing still. The speed of the train makes no difference to the speed of the light, and if someone on the train shines a beam of light forward, they also see it moving at 300,000 kilometers per second relative to themselves. Both observers, the one on the platform and the one on the train, see the light moving at the same speed, even though they are moving relative to each other at 200,000 kilometers per second. This seems contradictory. It seems impossible. How can both observers see the same beam of light moving at the same speed when they themselves are moving relative to each other?
The answer, Einstein realized, is that something else has to give. If the speed of light is the same for everyone, then space and time cannot be. The distances and durations that different observers measure must be different. Two people moving relative to each other will disagree about how long a second lasts, how long a meter is, and crucially, whether two events happened at the same time. Let us look at that last point, because it is the one that cuts deepest: the loss of simultaneity. Einstein devised a thought experiment that makes this vivid. Imagine three people riding in a fast-moving train.
One stands at the back of the carriage, one at the front, and one in the exact middle. The person in the middle has a device that emits a pulse of light in both directions simultaneously, toward the front and toward the back. From the perspective of the people on the train, everything is symmetrical. The light pulse travels from the middle to the back and from the middle to the front, covering equal distances. The light hits the back wall and the front wall at the same time. The person at the back and the person at the front raise their hands at the same instant, perfectly synchronous. Now imagine an observer standing on the platform watching the train speed by. This observer also sees the light pulse emitted from the middle of the carriage. But the train is moving. By the time the light reaches the back wall has moved forward toward the light. The light did not have to travel quite as far,
And by the time the light reaches the front wall has moved forward, away from the light. The light had to travel a little farther. Both the observer on the train and the observer on the platform agree on the speed of light. That is Einstein's second principle. The light moves at the same speed for both of them. But because the distances are different, the observer on the platform sees the light hit the back wall first and the front wall second. The two hands are not raised at the same time. The people on the train say the events were simultaneous. The person on the platform says they were not. And neither one is wrong. Simultaneity depends on who is doing the observing. This is not a trick of perception or a delay caused by light travel time. It is not that one observer is right and the other is mistaken. Both are equally correct from their own reference frames. Simultaneity itself is relative. There is no universal, absolute, at the same time.
What counts as now depends on how you are moving. Let that settle for a moment, because it sounds abstract, but its implications are concrete and personal. You might be lying next to someone right now, a partner, a pet, a sleeping child. In everyday life, you assume that your now and their now are the same. You are experiencing the same moment together. But if one of you were moving relative to the other at a significant fraction of the speed of light, your nows would be different. You would disagree about which events in the distant universe are happening right now. Your slices of now would be tilted, like cutting a loaf of bread at different angles. At everyday speeds, the differences are so vanishingly tiny that they are utterly undetectable. That is why Newton's absolute time worked so well for so long. At the speeds we encounter in daily life, walking, driving, flying, time dilation and the loss of simultaneity are so small that they might as well be zero.
Newton's clock, ticking uniformly for everyone, is a superb approximation. But it is only an approximation, and when speeds get close to the speed of light, the approximation breaks down and the true nature of time reveals itself. Einstein published his special theory of relativity in 1905, the same miraculous year that he explained Brownian motion and the photoelectric effect. He was 26. He was working at the patent office because he could not get an academic job, and with this one paper, he rewrote the foundations of physics. A few months later, Einstein published a short follow-up paper that contained the most famous equation in the history of science. E equals mc squared. Energy equals mass times the speed of light squared. This equation says something profound. Mass and energy are the same thing. They are interchangeable. A small amount of mass corresponds to an enormous amount of energy, because the speed of light squared is a very large number.
1 kilogram of mass, fully converted to energy, would release about 90 quadrillion joules, enough to power a city for years. This is the energy that powers the sun. Deep in the sun's core, hydrogen nuclei are being fused into helium nuclei under the crushing pressure of the sun's own gravity. The helium nucleus is slightly less massive than the hydrogen nuclei that went into it. That tiny difference in mass, less than 1%, is converted into energy and radiated as sunlight. The warmth on your face on a summer afternoon is mass being converted into energy, 150 million kilometers away, exactly as Einstein's equation predicts. And this equation connects back to you, personally, in a way that is easy to miss. The atoms in your body were forged in the hearts of stars. The carbon, the oxygen, the nitrogen, the calcium, the iron, all of it was made by nuclear fusion in massive stars that lived and died billions of years ago, long before the Earth existed.
When those stars exploded, their ashes were scattered into space, and eventually, over millions of years, gravity gathered those ashes into new solar systems, new planets, new oceans, new cells, new people. You are made of stardust. The atoms in your left hand may have come from a different star than the atoms in your right hand. You are, quite literally, the universe reassembled, carbon that was once inside a star, now arranged into a pattern that can think about stars. The consequences that flowed from Einstein's two principles were startling. If the speed of light is the same for all observers, then time itself must behave differently for observers moving at different speeds. This effect is called time dilation, and it is not a theoretical curiosity. It is a measurable, experimentally verified fact of the universe. To see why time dilation follows from Einstein's principles, imagine the simplest possible clock. It is just two mirrors, facing each other, with a pulse of light bouncing back and forth between them. Each time the light hits a mirror, that counts as one tick. If the mirrors are 1 meter apart, the light takes a very specific amount of time to travel from one mirror to the other, about 3.3 nanoseconds. Tick, 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 tick. A perfectly regular clock, governed by the speed of light. Now put this clock on a spaceship moving past you at high speed. You are watching from outside, standing still. From your perspective, the light in the clock is not just bouncing straight up and down. It is also moving sideways, because the clock is moving. The light has to travel a diagonal path, from the bottom mirror to the top mirror, but shifted sideways because the whole clock has moved during the transit. A diagonal path is longer than a straight vertical path, but the light still travels at the same speed, because the speed of light is the same for everyone. So if the path is longer and the speed is the same, the light takes longer to make the trip. Each tick of the moving clock takes longer, as seen from your perspective. The clock on the spaceship runs slow. Not because it is broken, not because something is wrong with it. It runs slow because time itself, for the moving clock, passes more slowly than time for you. The faster the spaceship moves, the more pronounced the effect. As the speed approaches the speed of light, the ticks get longer and longer, and time for the moving clock slows to a crawl. And it is not just the clock. Everything on the spaceship is affected. The heartbeats of the astronauts, the ticking of their watches, the firing of their neurons, the decay of radioactive atoms, the aging of their cells. All of it slows down. From the perspective of someone watching from outside, the astronauts age more slowly. They live longer. Their clocks, both mechanical and biological, tick at a reduced rate. From the astronaut's perspective, of course, nothing feels different. Their clocks tick at 1 second per second. Their hearts beat at the usual rate. They do not feel like they are moving in slow motion. For them, everything is normal. It is you, the outside observer, whose clock seems to be running fast. This is the reciprocity of special relativity. Each observer thinks the other's clock is running slow. It sounds paradoxical, but it is not. Because the two observers are in different states of motion, and they can never directly compare their clocks without one of them changing their state of motion, which breaks the symmetry. Now, you might be thinking, this is all very interesting, but it is just a thought experiment. Surely we cannot actually see time running at different rates for different objects. But we can. And the evidence came from one of the most unexpected places imaginable. A subatomic particle that nobody asked for. In the 1930s, as physicists were building the first detailed picture of the subatomic world, they started finding particles in cosmic ray experiments that did not fit neatly into the emerging picture of matter. Cosmic rays are high-energy particles from deep space, protons and heavier nuclei that slam into the upper atmosphere at enormous speeds. When these cosmic bullets hit gas molecules in the atmosphere, they produce a spray of secondary particles, a cascade of debris from the collision. And in this debris, physicists started seeing something unfamiliar. It looked like an electron. It had the same electric charge. It interacted with matter in many of the same ways. But it was about 200 times heavier than an electron. And unlike the electron, which is stable and lasts forever, this new particle decayed after just 2/millionths of a second, falling apart into an electron and a pair of neutrinos. They called it the muon. And when the American physicist Isidore Rabi heard about it, he said something that has become one of the most quoted lines in the history of particle physics. Who ordered that? Nobody ordered it. Nobody expected it. It did not seem to serve any purpose in the structure of atoms or the behavior of matter. It was just there, an uninvited guest at the party of fundamental particles, and its existence was a headache for anyone trying to build a tidy theory of nature. But the muon turned out to be incredibly useful for testing Einstein's relativity because of a simple calculation that did not add up. Muons are created in the upper atmosphere, about 15 kilometers above the surface, when cosmic rays collide with air molecules. They are created moving at speeds very close to the speed of light, which sounds fast enough to cover 15 kilometers easily. But remember, muons only live for 2/millionths of a second. Even traveling at nearly the speed of light, they should only cover about 600 meters before decaying. They should disintegrate long before they reach the ground. And yet, physicists were detecting muons at the surface. Lots of them. The muons were traveling far beyond their expected range, surviving for much longer than they should, as if their internal clocks were running slow. And that is exactly what was happening. The muons were traveling so close to the speed of light that time dilation was significant. From our perspective, standing on the ground, the muons' internal clocks were running slow. Their 2-microsecond lifetime was stretched out, dilated, by the Lorentz factor, a mathematical expression that depends on speed and grows unbounded as you approach the speed of light. At 99% of the speed of light, the Lorentz factor is about 7. At 99.9%, it is about 22. The muons' lifetimes, as measured by our clocks, were much longer than 2 microseconds, long enough for them to reach the ground. And there is a flip side to this. If you could ride alongside a muon, travel with it at the same speed, you would see it living for its normal 2 microseconds, no more, no less. But from the muon's perspective, the distance from the upper atmosphere to the ground would be contracted. The 15 kilometers would be squeezed down to a few hundred meters, because length contracts along the direction of motion at high speeds, just as time dilates. From the muon's point of view, it does not live longer. The ground just got closer. Both descriptions are correct. Time dilation and length contraction are two sides of the same relativistic coin. The muon, from our perspective, lives longer because its clock runs slow. The muon, from its own perspective, travels a shorter distance because space is compressed. The physics is consistent, but the experience of reality depends on your frame of reference. This was not just a thought experiment or a mathematical curiosity. These muons were being detected at the surface of the Earth, in real experiments with real detectors. The time dilation predicted by Einstein's special relativity was being confirmed by particles raining down from the sky. And then came even more direct evidence. In 1971, two physicists named Joseph Haffel and Richard Keating loaded 4 cesium atomic clocks onto commercial airliners and flew them around the world. One set of clocks flew eastward, one flew westward. When the traveling clocks were compared to clocks that had stayed on the ground, they disagreed. The clocks that had flown eastward, in the direction of the Earth's rotation, had lost a tiny amount of time. The clocks that had flown westward had gained a tiny amount of time. The differences were absurdly small, just a few hundred nanoseconds, billionths of a second. But they matched the predictions of relativity with impressive precision. And these were not subatomic particles, these were clocks, actual clocks, sitting in the overhead bins of commercial airplanes, ticking at different rates because they were moving at different speeds and at different altitudes. The speed effect is special relativity. Clocks moving faster tick slower. But there was also a gravitational effect, which comes from general relativity, Einstein's later and even more revolutionary theory, which we are about to get to. Clocks at higher altitudes, farther from the Earth's gravitational pull, tick slightly faster than clocks at lower altitudes. The Haffel-Keating experiment measured both effects, and both matched Einstein's predictions. There is a famous thought experiment that makes time dilation personal. It is called the twin paradox. Imagine two twins, identical in every way.
One stays on Earth. The other boards a spaceship and blasts off at 90% of the speed of light, traveling to a distant star and back. Because of time dilation, time passes more slowly for the traveling twin. When they reunite, the traveling twin is younger. They have aged less. Their hair is less grey. Their cells have divided fewer times. Their heart has beaten fewer times. They have lived fewer subjective seconds. The stay-at-home twin has been waiting, aging normally, and when the traveler returns, the twins are no longer the same age. The difference depends on the speed and duration of the trip. At 90% of the speed of light, the Lorentz factor is about 2.3, so the traveling twin would age roughly 2 years for every 5 years that pass on Earth. At 99%, the factor is about 7. At 99.9%, it is about 22. This sounds paradoxical because of the reciprocity we discussed earlier.
Each observer sees the other's clock running slow. So why does the traveling twin come back younger? Why not the stay-at-home twin? The resolution is that the situation is not symmetric. The traveling twin changes direction. They accelerate to leave, decelerate and turn around at the distant star, and accelerate again to return. The stay-at-home twin does none of this. The traveler changes reference frames, and the physics of changing reference frames is not the same as the physics of staying in one frame. It is the traveler who ages less. This has been confirmed by experiment repeatedly. The twin paradox is not a paradox at all, it is a fact. Today, time dilation is not a theoretical curiosity. It is a practical reality that affects technology you use every day. The Global Positioning System, GPS, relies on a constellation of satellites orbiting the Earth, each carrying extremely precise atomic clocks.
These clocks are affected by both special relativistic time dilation. The satellites are moving at about 14,000 kilometers per hour, and general relativistic time dilation. The satellites are farther from the Earth's gravitational field. Without corrections for these effects, the clocks on the satellites would drift away from clocks on the ground by about 38 microseconds per day. That sounds tiny, but it adds up to a positional error of about 10 kilometers per day. Your GPS would be useless within hours. So every GPS satellite carries clocks that are pre-adjusted to run at a slightly different rate than ground clocks, compensating for the relativistic effects. Every time your phone tells you where you are relying on Einstein's relativity. The theory of space and time that seemed so abstract and philosophical is built into the infrastructure of modern life.
But if special relativity shattered the idea of absolute time, it was what came next that shattered the idea of time as a smooth, featureless river. Because Einstein immediately realized that his special theory had a problem, a gap, a gaping hole where one of the most important things in the universe should be. And filling that hole would take him 10 years, nearly break him, and produce what many physicists consider the deepest theory in the history of science. The problem was gravity. Newton's theory of gravity was one of the most successful theories in the history of science. It described how every object in the universe attracts every other object with a force that depends on their masses and the distance between them. It predicted the orbits of planets, the paths of comets, the behavior of tides, the trajectories of cannonballs. It was powerful, elegant, and practical. But it depended on something that Einstein's special relativity had just destroyed. Newton's gravitational force acts instantaneously across space. When the sun pulls on the Earth, in Newton's picture, the pull happens right now, at this very instant, across the 93 million miles between them. If the sun were to suddenly vanish, the Earth would feel the change immediately. There would be no delay. The gravitational signal would travel at infinite speed. But special relativity says nothing can travel faster than light. Not matter, not energy, not information, not influence of any kind. If the sun vanished, the information about its disappearance could not reach the Earth faster than the speed of light, which takes about 8 minutes to cross the gap. For 8 minutes, the Earth would continue orbiting as though nothing had happened. Newton's gravity was incompatible with Einstein's relativity, and the problem went deeper than just the speed of gravitational influence. Newton's gravity depends on the distance between two masses right now, at the same time. But special relativity had just shown that, at the same time, depends on who is observing. There is no universally agreed now. So which distance should you use? Which now is the right one? Einstein knew that Newton's gravity had to be replaced with something new, something that was compatible with relativity. And this is where things get remarkable, because the path to the new theory began not with mathematics, but with a thought. In 1907, 2 years after publishing Special Relativity, Einstein was sitting in his chair at the patent office in Bern, thinking about gravity, and he had what he later called the happiest thought of his life. He imagined a person falling from the roof of a building. While falling, Einstein realized the person would not feel their own weight. They would feel weightless. If they let go of a ball, the ball would not fall away from them. It would float beside them, because both the person and the ball are accelerating toward the ground at the same rate. Inside the little world of the falling person, gravity has effectively disappeared. Now think about the reverse. Imagine you are in a closed box floating in deep space, far from any planet or star, in zero gravity. You feel weightless. Objects float beside you. Then someone attaches a rocket to the bottom of the box and fires it, accelerating the box upward at exactly 9.8 meters per second squared, the same acceleration as Earth's gravity. What would you feel? You would feel yourself being pushed toward the floor of the box. Objects would fall if you released them. If you stood on a scale, it would read your normal weight. Everything would feel exactly like standing on the surface of the Earth. You could not tell the difference.
No experiment you could perform inside the box would reveal whether you were in a gravitational field or in an accelerating rocket. This is the equivalence principle, the complete physical equivalence between gravity and acceleration. Einstein elevated this from a curious observation to a bedrock law of nature. He said that gravity and acceleration are not just similar, they are the same thing. There is no experiment that can distinguish between them. And this simple insight, this equivalence, led Einstein to a prediction so strange that even he found it hard to believe at first. If gravity and acceleration are equivalent, then anything that happens in an accelerating reference frame must also happen in a gravitational field. And one of the things that happens in an accelerating reference frame is that light bends. Imagine that you are in the accelerating box in space. Someone shines a beam of light horizontally through a small window on one side.
In the time it takes the light to cross the box has accelerated upward. So from your perspective, inside the box, the beam of light appears to curve downward. It does not travel in a straight line across the box. It follows a curved path, bending toward the floor. If gravity and acceleration are equivalent, then the same thing must happen in a gravitational field. Light passing through a gravitational field must bend. It must curve. Gravity must affect light. This was a startling prediction. Light has no mass. In Newton's theory, gravity only acts on objects with mass. Light should be completely unaffected by gravity. But Einstein's equivalence principle demanded otherwise, and the prediction would eventually be confirmed in one of the most celebrated experiments in the history of science. Einstein actually made an early attempt to calculate the deflection of light in 1911, 4 years before general relativity was complete.
Using a simplified version of his theory, he predicted that starlight passing near the Sun would be deflected by about 0.87 arc-seconds. This early calculation was half the correct value, because it only accounted for the curvature of time and not the curvature of space. The full answer, which required the complete machinery of general relativity, would turn out to be exactly twice as large, 1.75 arc-seconds. In a strange twist of fate, an eclipse expedition was organized in 1914 to test Einstein's prediction before general relativity was finished. A team of German astronomers traveled to Crimea to observe the solar eclipse of August 21, 1914. But World War I broke out just weeks before the eclipse. The astronomers were detained by Russian authorities as enemy nationals, their equipment was confiscated, and the expedition was abandoned.
This was, in retrospect, one of the luckiest failures in the history of science.
If the 1914 expedition had succeeded, they would have measured a deflection of 1.75 arc-seconds, which would have contradicted Einstein's 1911 prediction of 0.87 arc-seconds. Einstein might have been declared wrong, and the entire trajectory of 20th century physics might have been altered. Instead, the failed expedition gave Einstein 3 more years to complete his theory, to realize that the correct prediction was 1.75 arc-seconds, and to be triumphantly confirmed when Eddington finally made the measurement in 1919. But light bending was just the beginning. Einstein pushed the equivalence principle further, and it led him somewhere even more profound.
If gravity bends light, and if light is the fastest thing in the universe, the yardstick by which all distances and durations are measured, then gravity must bend space and time themselves. Not metaphorically, literally. The fabric of space-time, the four-dimensional stage on which all of physics plays out, must be curved, warped, distorted by the presence of mass and energy. This was the core insight of general relativity. Gravity is not a force. It is geometry. It is the curvature of space-time. Massive objects do not reach out and pull on each other across the void. Instead, they curve the space-time around them, and other objects move along the curves. Think of a heavy bowling ball sitting in the middle of a stretched rubber sheet. The ball creates a dip, a curve in the sheet. If you roll a marble across the sheet, the marble does not travel in a straight line. It curves, following the contour of the dip, spiraling toward the bowling ball.
From a distance, it looks like the bowling ball is pulling the marble toward it. But there is no pull. The marble is simply following the curvature of the sheet. This analogy is imperfect because it only shows the curvature of space, not space-time, and it still needs an external gravity to make the bowling ball create the dip. But it captures the essential idea. Mass curves space-time. Objects follow the curves. What we perceive as the force of gravity is really just the geometry of the universe. Developing this insight into a complete mathematical theory took Einstein 10 years of grueling work. 10 years. From 1905, when he published Special Relativity, to 1915, when he finally wrote down the field equations of general relativity, Einstein wrestled with the most difficult problem he had ever faced. The trouble was that describing curved spacetime requires extremely advanced mathematics. Not the algebra or calculus that Einstein was comfortable with, but the mathematics of curved surfaces and higher dimensional geometry, a branch of mathematics called differential geometry, developed in the 19th century by the German mathematician Bernhard Riemann. Einstein needed Riemannian geometry, tensor calculus, covariant derivatives, Christoffel symbols, all of it, and he did not know any of it. He turned to his old friend Marcel Grossmann, a mathematician who had been his classmate at the Swiss Federal Polytechnic. Grossmann had been the organized, diligent student who took meticulous notes in class, while Einstein skipped lectures. Now Einstein needed those notes, and more. He reportedly wrote to Grossmann saying that he was working on a problem of enormous importance and begging for mathematical help, adding that he would go crazy without it. Grossmann taught Einstein the mathematics of curved spaces, and together they published a preliminary version of the theory in 1913. But it was not quite right. The equations were not fully general. They did not work in all coordinate systems, which meant they violated the very principle of general covariance that Einstein had set out to establish. Einstein spent 2 more years trying to fix the equations, making mistakes, publishing wrong versions, retracting them, starting over. The final push came in November 1915, one of the most intense periods of intellectual effort in human history. Einstein was racing against time, and also, he feared, against the great German mathematician David Hilbert, who had attended Einstein's lectures on general relativity in June 1915 and had independently begun working on the field equations using a more elegant mathematical approach. Einstein was terrified that Hilbert would solve the problem first. Between November 4th and November 25th, 1915, Einstein presented 4 papers to the Prussian Academy of Sciences, each one refining and correcting the previous one, each one getting closer to the final answer. He barely slept. He barely ate. He was, by his own account, in a state of intense intellectual agitation, his body racked with stomach pains from the stress. By November 25th, 1915, after years of false starts, wrong turns, and near breakdowns, Einstein had the final equations. The field equations of general relativity, a set of mathematical relationships that describe how the distribution of mass and energy determines the curvature of spacetime, and how the curvature of spacetime determines the motion of mass and energy. One of the first things Einstein did with his new equations was calculate the orbit of Mercury. Mercury, the closest planet to the Sun, has an orbit that does not quite follow Newton's predictions.
Its elliptical orbit rotates slowly around the Sun, a phenomenon called the precession of the perihelion. Newton's gravity predicted most of this precession, but not all of it. There was a tiny discrepancy, about 43 arc-seconds per century, that had puzzled astronomers for decades. Einstein plugged the numbers into his new equations and got the right answer. Exactly 43 arc-seconds per century. No fudge factors, no adjustments. The math just worked. Einstein later said that when he saw the result, he had heart palpitations. He was so excited that he could not sleep for days. After 10 years of struggle, after years of wrestling with the most difficult mathematics he had ever encountered, his theory was confirmed by a measurement that had been sitting in the astronomical tables for half a century, waiting for the right theory to explain it. And then came the prediction that would make Einstein a global celebrity. General relativity predicted that light passing near a massive object would be deflected, bent by the curvature of space-time. Einstein calculated that starlight passing near the edge of the Sun should be deflected by a specific amount, 1.75 arc-seconds. This was twice the value predicted by a simpler Newtonian calculation, and the difference was large enough to be measurable. But to see starlight near the Sun, you need to block out the Sun's overwhelming brightness. You need a solar eclipse. In 1919, 4 years after Einstein published his equations, a British astronomer named Arthur Eddington organized 2 expeditions to observe a total solar eclipse. One went to the island of Principe, off the west coast of Africa. The other went to Sobral, in Brazil. Their goal was to photograph stars near the edge of the Sun during the eclipse and measure whether their apparent positions had shifted, deflected by the curvature of space-time around the Sun. Eddington was a Quaker and a conscientious objector during World War I. He had been exempted from military service, partly because of his scientific importance, and partly because the Astronomer Royal, Frank Dyson, argued that the eclipse expedition was of vital national interest. There is something striking in this. A British pacifist traveling across the world to test the theory of a German-born physicist in the immediate aftermath of a war between Britain and Germany. The eclipse happened on May 29, 1919. On Principe, the weather was terrible. Clouds and rain plagued the team throughout the day. But at the critical moment, just as the eclipse reached totality, the clouds thinned enough to take photographs. In Sobral, the weather cooperated more fully and the team got clearer images. When the photographs were developed and the stellar positions were measured, the results matched Einstein's prediction. The starlight had been deflected by the amount that general relativity required. Space-time was curved. The announcement of the results in November 1919 made Einstein world-famous overnight. Newspapers around the world carried the story. Einstein went from being an obscure physicist, known mainly to specialists, to being the most famous scientist in the world, a position he has held in the public imagination ever since. And with general relativity confirmed, the implications for time became even more dramatic. Special relativity had shown that time runs differently depending on how fast you are moving. General relativity added a new dimension. Time also runs differently depending on how strong the gravitational field is around you. Near a massive object, where space-time is strongly curved, time runs slower. Farther away, where space-time is flatter, time runs faster. This is gravitational time dilation.
And like its special relativistic cousin, it has been confirmed by experiment after experiment. The clocks on GPS satellites run faster than clocks on the ground, because they are farther from the Earth's gravitational field. The difference is tiny, about 45 microseconds per day gained due to the weaker gravity, partially offset by the 7 microseconds per day lost due to the satellite's orbital speed. The net effect, about 38 microseconds per day, is enough to wreak havoc on GPS accuracy if it is not corrected for. Closer to Earth, the effect has been measured directly. In 2010, physicists at the National Institute of Standards and Technology used ultra-precise optical clocks to measure the time dilation between two clocks separated by a height difference of just 33 centimeters, less than the length of your forearm, and they found a measurable difference. The lower clock, 33 centimeters closer to the Earth, was ticking slightly slower than the upper clock. Your feet are closer to the center of the Earth than your head, so your feet are in a slightly stronger gravitational field. And that means your feet age slightly slower than your head. The difference is inconceivably tiny, far too small to affect your health or your lifespan. But it is real. It is measurable. It is a fact about the universe. The passage of time is utterly personal. Your clock, whether it is a mechanical watch or the biological rhythms of your body, ticks at a rate that depends on where you are and how you are moving. Someone standing on top of a mountain ages slightly faster than someone standing in a valley. Someone in a jet plane ages slightly differently from someone sitting still. And the differences, while tiny on Earth, become enormous in extreme conditions. Near a black hole, where gravity is unimaginably intense, time dilation becomes dramatic. If you were to hover near the event horizon of a black hole, time for you would slow to a crawl relative to the rest of the universe. Minutes might pass for you, while years or centuries pass outside. You could, in principle, use this as a form of one-way time travel into the future. Hang out near a black hole for a while, and when you leave, the rest of the universe will have aged far more than you have. And there is another confirmation of general relativity that deserves mention, because it speaks to how alive space-time really is. In 2015, exactly 100 years after Einstein published his field equations, physicists at the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time. Gravitational waves are ripples in space-time itself, produced when massive objects accelerate violently. Two black holes spiraling into each other, for example, send out waves of space-time distortion that travel outward at the speed of light, like ripples from a stone dropped into a pond. As these waves pass through space, they stretch and squeeze everything in their path. They stretch the distance between objects in one direction and compress it in the perpendicular direction, then reverse, oscillating back and forth. The gravitational waves LIGO detected in September 2015 were produced by two black holes, each about 30 times the mass of the Sun, spiraling into each other and merging over 1 billion light-years away. The merger happened over 1 billion years ago, and the ripples in space-time had been traveling toward Earth ever since. When they arrived, they stretched and compressed LIGO's 4-kilometer-long detector arms by a distance of about 1/10,000th the diameter of a proton. That is how sensitive the instrument had to be, and it worked. Space-time is not a passive stage on which events happen. It is a dynamic, flexible, physical thing that responds to mass and energy, curves and ripples and waves. The mattress you are lying on is sinking slightly into the curvature of space-time around the Earth. And right now, at this very moment, gravitational waves from colliding neutron stars and merging black holes across the universe are passing through your body, stretching and compressing you by distances far too small for any human sensation to detect, but real, measurably real. A physical massage from the cosmos. In 2023, astronomers published a striking study of distant quasars, incredibly bright objects powered by supermassive black holes in the centers of distant galaxies. These quasars are so far away that their light has been traveling for billions of years. By analyzing the flickering of these quasars, the astronomers found something predicted but never before observed so clearly. The ticking rate of the quasar clocks was slower than clocks today. When the universe was 1/10 of its current age, time appeared to tick at 1/5 of its current rate. This is exactly what general relativity predicts. The expansion of the universe stretches the light from distant objects, and it stretches time too. Time in the distant past really did tick differently, as seen from our perspective. Time dilation around black holes and time dilation in the distant past, despite the vastly different contexts in which they arise, are effectively the same phenomenon. The curvature of space-time, whether caused by a nearby mass or by the expansion of the cosmos, distorts the passage of time. And so, from the earliest decades of the 20th century, our vision of time was changed forever. In Einstein's revolutionary view of the universe, the passage of time is yours and yours alone. Your clock, be it mechanical like a watch or biological like the beat of your heart, ticks at its own rate. 1 second per second for you, always. But other people's clocks can tick at radically different rates relative to yours, if they are moving differently, sitting in a different gravitational field, or located in a different epoch of the universe's life. This bending of time is truly part of the cosmos. The muons smashing into the surface of the Earth are a testament to it. The atomic clocks taken for journeys around the world confirm it. The GPS corrections that keep your phone's navigation accurate depend on it. And all of this leads to a question that sounds strange, but follows directly from Einstein's equations. A question that has haunted physicists and philosophers ever since general relativity was published.
If time is not universal, if now is different for different observers, if the past and the future are just different regions of the same four-dimensional space-time, then is the past really gone? Is the future really unwritten? Or are they all out there, equally real, equally existing, like pages in a book that has already been printed? Let us go back to Isaac Newton for a moment. Back to the apple tree in Woolsthorpe, back to 1666, back to the plague year and the solitary young man thinking about the nature of the universe. Newton's equations of motion are deterministic, completely, absolutely, perfectly deterministic. If you know the position and velocity of every particle in the universe at any given moment, Newton's laws let you calculate the position and velocity of every particle at any other moment, past or future. The future is completely determined by the present, and the present is completely determined by the past. In Newton's universe, with its absolute time and its deterministic laws, the past is just as calculable as the future. If you had perfect knowledge of the present, you could run Newton's equations backward and reconstruct the past in every detail, just as you could run them forward and predict the future in every detail. This raises a strange question. If the past and the future are both completely determined by the present, are they less real than the present? In some sense, the realities of the past, present, and future all exist. They are all calculable. They are all inevitable. The present is just a particular moment that happens to be the one you are experiencing right now. But there is nothing special about it from the point of view of the physics. Newton's equations do not distinguish now from any other moment. You have to tell them when now is. The equations themselves are indifferent.
This idea, strange and unsettling in Newton's framework, returned with full force in Einstein's relativity. In special relativity, each particle in the universe traces out a path through four-dimensional space-time. 3 dimensions of space and 1 of time. This path is called the particle's world line. It records where the particle is at every moment of its existence, from its creation to its destruction, or to the end of time, laid out as a continuous curve in the four-dimensional fabric. And like Newton's universe, Einstein's universe is deterministic. The equations of general relativity, given the distribution of mass and energy at one moment, determine the entire past and future of the universe. The world lines of every particle are fixed. The history of the cosmos is written in the geometry of space-time. And here is the crucial point. In Einstein's relativity, there is no universally agreed now. Different observers, moving at different speeds, slice space-time into past, present, and future differently. What you call now is a three-dimensional slice through the four-dimensional space-time. But another observer, moving relative to you, would slice it at a different angle, and their now would include events that you would call past and events that you would call future. If both slices are equally valid, if there is no physical reason to prefer one over the other, then it seems like the events in your future are already out there, already existing in the space-time, just as the events in your past are. They have not happened yet, from your perspective, but they are there, in the four-dimensional structure, waiting for your world line to reach them. This view of the universe is called the block universe. The idea is that all of space-time, past, present, and future, exists as a single, static, four-dimensional block. Nothing is created. Nothing is destroyed.
Nothing moves through time. Instead, the block just is. And what we experience as the flow of time is an illusion, a subjective sensation produced by the fact that our consciousness moves along our world lines, experiencing each event in sequence. The mathematics of general relativity supports this picture quite strongly. Einstein's equations are unequivocal. They describe a four-dimensional space-time in which the past and the future are just as real as the present. There is nothing in the equations that singles out a particular moment as now. The equations are timeless. They describe the entire history of the universe, from beginning to end, as a single mathematical object. Einstein himself seemed to accept this view. After the death of his close friend Michel Besso in 1955, just weeks before his own death, Einstein wrote a letter to Besso's family. In it, he said that the distinction between past, present, and future is only a stubbornly persistent illusion. Think about what that means. According to this view, the version of you that was 7 years old is still there, in the block, experiencing the 7th year of your life. The version of you that will be 80 is already there too, experiencing whatever that future holds. You do not flow through time. Time does not flow at all. The block is static. You are a world line, a four-dimensional structure embedded in a four-dimensional universe. And what you experience as now is just the point along your world line where your consciousness happens to be focused. This is deeply counterintuitive. It goes against everything you feel about time. You feel that the past is gone, that the future is open, that the present is the only moment that really exists. You feel that you make choices, that the future depends on what you decide, that you have free will. The block universe seems to undermine all of that.
If the future is already out there, already fixed, already written in the geometry of space-time, then what room is there for choice, for agency, for the feeling that your life is unfolding, moment by moment, in a way that is not predetermined? Many physicists have struggled with this. Some embrace the block universe and accept that free will is an illusion. Others reject the block universe and argue that the flow of time is real, that the present is genuinely special, that the future is genuinely open, and that the timeless picture suggested by the equations is just a mathematical artifact that does not capture the full reality. The question of free will, in particular, has haunted the block universe discussion. In the 1980s, the American neuroscientist Benjamin Libet designed an experiment to test the timing of conscious decision-making. He asked subjects to flex their wrist at a moment of their choosing while monitoring their brain activity with electrodes. And he found something disturbing. About half a second before the subjects reported feeling the urge to flex, a characteristic electrical signal, the readiness potential, appeared in their brains. The brain was preparing to move before the person was conscious of deciding to move. Libet's experiment has been endlessly debated, criticized, refined, and repeated. Some researchers have argued that the readiness potential is too noisy and variable to serve as a reliable marker of unconscious decision-making. Others have found that more sophisticated, brain scanning techniques can predict a subject's decision up to 7 seconds before they are aware of making it. The implications are deeply unsettling. If your brain begins preparing an action before you are conscious of choosing it, where does the choice actually happen? Are you the author of your decisions? Or are you a spectator watching decisions your brain has already made?
In the block universe, this question takes on an even sharper edge. If the future is already determined, if your world line through space-time is fixed, then the feeling of making a choice is itself part of the block, a predetermined event that was always going to happen exactly the way it did. Your sense of agency, the feeling that you could have done otherwise, would be an illusion generated by a brain that does not have access to the full four-dimensional picture. But many philosophers and scientists push back against this conclusion. They argue that free will does not require the ability to have done otherwise. It only requires that your actions flow from your own desires, beliefs, and character, rather than being coerced by external forces. A block universe is compatible with this kind of free will, because even in a block universe, your actions are determined by your own brain states, not by someone else's.
You are still the one doing the choosing, even if the outcome was always going to be what it was. Others take a different approach entirely. They argue that the block universe picture, for all its elegance, is incomplete. It captures the physics of space-time beautifully, but it may miss something essential about the nature of the present moment, about the experienced quality of now, about the way time feels from the inside. And then there is a third possibility, one that tries to hold both pictures together. Quantum mechanics, as we discussed earlier, is genuinely probabilistic. The future in quantum mechanics is not determined by the present. The wave function gives you probabilities, not certainties. When a quantum measurement is made, the outcome is genuinely random, at least as far as quantum mechanics can tell. The future is not written in advance. So here is the tension. General relativity, Einstein's theory of gravity, gives us a block universe where past, present, and future are all equally real and determined. Quantum mechanics, the theory of the very small, gives us a universe where the future is genuinely open, where outcomes are not predetermined, where randomness is fundamental. These two theories are the two greatest achievements of 20th century physics. They are both wildly successful in their respective domains. General relativity describes the large-scale structure of the universe. Quantum mechanics describes the behavior of atoms and subatomic particles. Both have been tested to breathtaking precision, and both have never failed. But they are incompatible. They use different mathematical languages, make different assumptions about the nature of reality, and give contradictory answers when you try to apply them to the same situation, such as the interior of a black hole or the first instant of the Big Bang.
Reconciling these two theories, finding a single framework that encompasses both gravity and quantum mechanics, is the great unsolved problem of modern physics. And some of the ideas that have emerged from this quest have profound implications for our question about time and identity. One of these ideas comes from a theory called loop quantum gravity. This is one of the leading candidates for a quantum theory of gravity, and it offers a picture of reality that is radically different from either the smooth spacetime of general relativity or the probability waves of standard quantum mechanics. In loop quantum gravity, space and time are not smooth and continuous. They are made of tiny, discrete pieces, basic building blocks of geometry, woven together in a complex network. Think of reality as a tapestry, a fabric woven from tiny loops of quantized geometry. At the scale of everyday life, the tapestry looks smooth and continuous, just as a piece of cloth looks smooth when you hold it at arm's length. But zoom in, down to the smallest possible scale, about a billionth of a trillionth of a trillionth of a meter, and the individual threads become visible. Space is granular. Time is granular. Reality is woven, not poured. And in this picture, time has a special role. The past, in loop quantum gravity, is the finished tapestry, the part that has already been woven. The future is the unwoven thread, the material that has not yet been incorporated into the fabric. And now, this moment, the present, is the edge of the weave, the point where the new thread is being added, where the unknown future is being knitted into the known past. In this picture, the block universe is not quite right. The past is real, solidified into the fabric. The future is genuinely open, not yet woven. And the present is not just a subjective illusion. It is the busy, active frontier where space-time itself is being constructed. This is speculative. Loop quantum gravity is not yet a complete theory, and it has not been experimentally confirmed. But it offers a perspective on time that resonates with our experience in a way that the block universe does not. It says that time is real, that the present is special, that the future is genuinely undetermined, and that you, right now, are at the edge of reality, at the point where the universe is being made. Whether the universe is a static block or a growing tapestry, whether the future is written or unwritten, the fact remains that time, the medium through which you experience your existence, is not the simple, universal, steadily flowing river that your intuition tells you it is. It bends, it stretches, it depends on where you are and how you are moving. And its deepest nature remains one of the great open questions in physics. And this brings us back to the question we started with, the question about you. We have been peeling away layers all night. We started with your body and found it was constantly replacing itself, a biological ship of Theseus. We went deeper to the atoms and found they were mostly empty. We went deeper still to the quantum level and found that the particles inside your atoms are not really particles at all, but probability waves entangled with each other across cosmic distances, without definite properties until they are measured. And we looked at time, the medium of your experience, and found it is flexible, personal, curved, and possibly not even basic. So what holds it all together? What are the deepest rules? Modern physics describes the basic forces and particles of nature using a framework called quantum field theory. This is the language of the standard model of particle physics, the most precise and successful theory in the history of science. In quantum field theory, the deepest stuff of the universe is not particles. The deepest stuff is fields. Fields that permeate all of space, filling every cubic centimeter of the cosmos with their quiet, invisible presence. Think of these fields as being a bit like the surface of an ocean. When the ocean is calm, it looks flat and featureless. But disturb it, add energy, and waves appear. Ripples and swells that travel across the surface interact with each other, combine and separate. The quantum fields are like that, except they fill all of space, not just a surface. When these fields are in their calm, lowest energy state, you might call the state empty. But it is not truly empty. The fields are still there, humming quietly, ready to be excited. And when they are excited, when energy disturbs them, the disturbances are what we see as particles. An electron is not a tiny ball. It is a vibration in the electron field, a localized ripple that behaves in many ways like a particle, but is really just the field doing something.
A photon is a vibration in the electromagnetic field. A quark is a vibration in one of the quark fields. Every basic particle in nature is a vibration in its corresponding quantum field. This is worth pausing on because it changes the picture completely. You are not made of little balls of matter stacked together like bricks in a wall. You are made of vibrations, patterns of excitation in underlying quantum fields. The electron field, the quark fields, the electromagnetic field, the gluon field, all of them singing together, their vibrations interacting and overlapping and combining to create the atoms and molecules and cells and organs and thoughts that make up you. And the interactions between these vibrations, the way one vibration in one field can excite a vibration in another field, are what we call the basic forces. When two electrons repel each other, what is really happening is that the vibrations in the electron field are exchanging vibrations in the electromagnetic field.
The exchanged vibration is a photon. The photon carries momentum from one electron to the other, pushing them apart. The same pattern applies to all the forces. The strong force, which holds quarks together inside protons and neutrons, is mediated by vibrations in the gluon field. The weak force, which is responsible for certain forms of radioactivity, is mediated by vibrations in the W and Z fields. And there is one more field, perhaps the most famous of all, the Higgs field. The Higgs field is unlike the others. It is not zero in its lowest energy state. Even in what we would call empty space, the Higgs field has a non-zero value. It fills all of space with a constant, uniform presence. And particles that interact with the Higgs field acquire mass. The stronger the interaction, the heavier the particle. Think of it like moving through thick air versus thin air. A particle that interacts strongly with the Higgs field is like someone trying to walk through molasses. They are slowed down, resisted, and that resistance is what we experience as mass. A particle that does not interact with the Higgs field at all, like the photon, moves through freely at the speed of light and has no mass. The Higgs boson, the vibration of the Higgs field, was predicted theoretically in the 1960s and finally discovered experimentally in 2012 at CERN, after a search that lasted nearly 50 years and required the largest, most complex machine ever built by human beings, the Large Hadron Collider. With the discovery of the Higgs boson, the standard model of particle physics was complete. Every particle it predicted had been found. Every interaction it described had been confirmed. It is a theory of stunning power and precision. And yet, gravity is not included in it. General relativity describes gravity as the curvature of space-time. Quantum field theory describes the other three forces as vibrations in quantum fields. These two descriptions are mathematically incompatible. You cannot simply write gravity as another quantum field and add it to the standard model. The math does not work. The equations blow up, producing infinities that cannot be removed. This is the deepest unsolved problem in physics. Finding a quantum theory of gravity, a single mathematical framework that encompasses both the curvature of space-time and the quantum nature of matter and forces, has been the holy grail of theoretical physics for nearly a century. And beneath all the technical difficulty, beneath all the competing theories and failed attempts, there is a question that has emerged with increasing urgency in recent decades. What if space-time itself is not bedrock? What if space and time are not the bedrock of reality, but something that emerges from a deeper layer, the way the temperature of a gas emerges from the collective motion of billions of molecules?
Each molecule has a position and a velocity, but none of them has a temperature. Temperature is an emergent property, a statistical average that only makes sense when you zoom out and look at the whole collection. Some physicists believe that space-time might be like that at the deepest level there is no space and no time, just some more fundamental structure, perhaps a network of quantum entanglement, perhaps a mathematical abstraction, from which space and time and matter and forces all emerge as large-scale approximations. The most developed version of this idea comes from the physics of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered something remarkable about black holes. The entropy of a black hole, the measure of its internal disorder, is proportional not to its volume, but to the area of its event horizon, the spherical boundary beyond which nothing can escape.
This was surprising, because for every other physical system, entropy scales with volume. A box twice as large can hold twice as much disorder, but a black hole twice as large has 4 times the entropy, because entropy scales with the surface area, not the interior. This led to the holographic principle, proposed by Gerard 't Hooft and Leonard Susskind. The idea that the maximum amount of information that can be contained in any region of space is determined by the surface area of that region, not its volume. All the information about what is happening inside a volume of space can, in principle, be encoded on its boundary, like a hologram that projects a 3-dimensional image from a 2-dimensional surface. If the holographic principle is correct, then the 3-dimensional reality you experience might be a projection, an emergent phenomenon arising from information encoded on a distant 2-dimensional surface. The depth of space, the sense that things are near and far, might be something that emerges from a more fundamental, lower-dimensional description. John Archibald Wheeler, one of the towering figures of 20th century physics, a man who coined the terms black hole and wormhole and mentored Richard Feynman, spent the last decades of his career thinking about these questions, and he came to a remarkable conclusion. He said that the universe is not made of matter or energy at its deepest level. It is made of information. He coined the phrase "it from bit," meaning that every particle, every field, every force derives its existence from information, from the answers to yes or no questions, from bits. Wheeler went even further. He proposed what he called the participatory universe, the idea that observers are not passive spectators of reality, but active participants in its creation.
The quantum act of observation, the collapse of the wave function, is not just revealing a pre-existing reality, it is creating reality. The universe, in Wheeler's view, is a self-excited circuit. It creates observers, and the observers, through their measurements, create the universe. The past, the future, the
the very fabric of spacetime, are brought into existence by the act of observation. This is a radical idea, and most physicists do not take it literally. But it captures something deep about the relationship between consciousness and reality, between the observer and the observed, that quantum mechanics has been hinting at since the earliest days of the theory. And it connects to something we encountered earlier in our journey, the question of symmetry. A sphere is symmetrical. You can rotate it any way you like, and it still looks the same. This seems like a simple observation, a matter of aesthetics. But in physics, symmetry has surprising consequences.
In 1915, the same year Einstein published General Relativity, a German mathematician named Emmy Noether proved something remarkable. She showed that every symmetry of the laws of physics corresponds to a conserved quantity, a quantity that cannot be created or destroyed. If the laws of physics do not change when you move your experiment 1 meter to the left, that is a symmetry under translation. And Noether showed that this symmetry implies the conservation of momentum. Momentum cannot simply vanish. It has to go somewhere. One billiard ball transfers its momentum to another. If the laws of physics do not change when you rotate your experiment by 90 degrees, that is another symmetry. And Noether showed that this symmetry implies the conservation of angular momentum, the conservation of spin. And if the laws of physics do not change over time, if performing your experiment today gives the same result as performing it tomorrow, that is yet another symmetry, a symmetry under time translation. And this symmetry implies the conservation of energy. Energy cannot be created or destroyed, it can only change form. These are not minor results. Conservation of energy, conservation of momentum, conservation of angular momentum, the most fundamental rules of physics, are all consequences of symmetry. They are not arbitrary rules imposed on the universe from outside. They follow from the simple observation that the universe looks the same from different angles, at different locations, at different times. Symmetries run even deeper in quantum mechanics. The electromagnetic force is associated with a symmetry group called U1. The strong force is associated with a symmetry group called SU3. The weak force is associated with SU2.
These mathematical structures dictate which interactions can occur and which cannot. If the symmetry allows it, the interaction happens. If the symmetry forbids it, the interaction is impossible. The rule book of reality is written in the language of symmetry. And here is something that might seem contradictory, but is actually one of the most profound truths about the universe. Some of the symmetries of our universe are broken. They are not perfect, and if they were perfect, you would not exist. Think about the asymmetry between matter and antimatter. Every particle has an antiparticle, a mirror image version with opposite charge. When a particle meets its antiparticle, they annihilate each other, releasing energy. In a perfectly symmetric universe, the Big Bang would have created exactly equal amounts of matter and antimatter. Every electron would have had a corresponding positron, every proton a corresponding antiproton. And shortly after the Big Bang, all the matter and all the antimatter would have annihilated each other, leaving nothing behind. No atoms, no stars, no planets, no you. Just a featureless bath of radiation. But the universe is not perfectly symmetric. Some tiny imbalance in the laws of physics, favored matter over antimatter by about 1 part in a billion. For every billion matter-antimatter annihilations, 1 extra particle of matter was left over. And that 1 in a billion surplus is everything you see around you. Every atom in your body, every star in the sky, every galaxy in the cosmos, all of it is made from that tiny excess, that slight crack in the symmetry. The culprit seems to be the weak force, the oddest of the four fundamental forces. Unlike the other forces, the weak force distinguishes between left and right. All neutrinos spin in one direction, left-handed, while all antineutrinos spin the other way, right-handed. This is deeply strange.
No other force shows this kind of directional preference. And it is this left-right asymmetry, this crack in the otherwise beautiful symmetry of the basic forces, that seems to have given rise to the imbalance between matter and antimatter. You exist because the universe is imperfect. You exist because symmetry is cracked. The most beautiful mathematical structures in physics, the symmetry groups that describe the basic forces, are slightly flawed, and those flaws are the reason there is something rather than nothing. And there is a poignant human story behind this discovery of symmetry's role. Emmy Noether, the mathematician who proved the connection between symmetry and conservation laws, was one of the most important mathematicians of the 20th century, and one of the most unjustly overlooked. She was born in Germany in 1882, the daughter of a mathematics professor.
She showed unusual mathematical ability from an early age, but she was a woman, and women were not allowed to enroll at the University of Erlangen. She attended lectures anyway, as an unofficial auditor, and eventually earned her doctorate by special permission. In 1915, the same year Einstein published General Relativity, Hilbert and Felix Klein invited Noether to Göttingen, one of the world's great centers of mathematics, to work on the mathematical foundations of Einstein's new theory. But the philosophy faculty objected to a woman being given a teaching position. Hilbert was furious. "I do not see that the sex of the candidate is an argument against her admission as a lecturer," he said. "After all, we are a university, not a bathhouse." Noether was eventually allowed to lecture, though for years she did so under Hilbert's name, giving talks that were officially listed as his. She never received a proper salary from Göttingen, and yet, during this period of professional marginalization, she produced some of the most profound results in the history of mathematical physics. Her theorem, published in 1918, showed that every continuous symmetry of a physical system corresponds to a conserved quantity. That single insight unified a vast landscape of physical laws under a single mathematical principle. It remains one of the most elegant and far-reaching results in all of theoretical physics. In 1933, when the Nazis came to power, Noether was dismissed from her position because she was Jewish. She emigrated to the United States and took a position at Bryn Mawr College, where she continued to work until her sudden death from surgical complications in 1935. She was 53. Einstein wrote a tribute to her in the New York Times, calling her the most significant creative mathematical genius produced since the higher education of women began.
So where does all of this leave us?
What are we to make of a universe where the deepest rules are symmetries? Where the deeper stuff is vibrations in fields? Where space and time might not be fundamental? Where the distinction between past, present, and future might be an illusion? And where your very existence depends on an imperfection, a crack, a glitch in the cosmic code. Let us gather the threads. We started this journey with the Ship of Theseus, the ancient vessel whose planks were replaced, one by one, until nothing original remained. And we asked, is it still the same ship? We have spent this entire night showing that you, in every physical sense, are a ship of Theseus. Your cells are being replaced. Your atoms are being swapped out.
The stuff you are made of is not really stuff at all, but vibrations in quantum fields, probability waves that do not have definite properties until they are measured, entangled with particles across the cosmos.
existing in a space-time that bends and stretches and may not even be fundamental. And yet, through all of this, you persist. You wake up every morning and feel like the same person. You remember your past. You plan for your future. You have a sense of continuity, a sense of self, a sense that there is a you that has been you for as long as you can remember. Where does this persistence come from? The seat of consciousness, the location of the mind, has been a mystery for as long as humans have thought about it. The ancient Egyptians believed the heart was the center of all activity, the home of the soul, with thoughts radiating out to the body's extremities. Aristotle agreed, claiming the brain was too far from the center of things to be important.
For much of history, the relationship between mind and brain was simply unknown. In the 17th century, Descartes, the same man who watched the fly walk across his ceiling and invented coordinate systems, proposed that the brain and the mind were separate things. The brain was physical, made of matter, subject to the laws of physics. The mind was something else entirely, something immaterial, something that existed in a different realm and interacted with the physical brain through some mysterious mechanism. This view, known as dualism, held sway for centuries, and Gottfried Wilhelm Leibniz, a contemporary of Newton, supported Descartes with a thought experiment that remains vivid today. Imagine, Leibniz said, that you could shrink yourself down to the size of a flea and walk around inside a working brain. You would see biological machinery, neurons and connections and chemical processes, but you would not see thoughts. You would not see ideas bubbling away inside the fleshy material. You would not find love or creativity or the experience of the color red sitting there on a shelf. The mind, Leibniz concluded, must be something separate from the brain, something beyond the physical. But with the coming of the 20th century, dualism came under sustained attack. Advances in technology allowed scientists to observe the living brain in action. And what they discovered was that Leibniz's hypothetical journey through the brain was blind to seeing thoughts, not because thoughts exist in some other realm, but because thoughts are processes. They are patterns of activity distributed across vast networks of neurons, invisible to a tiny observer walking among the cells, just as a hurricane is invisible to a single raindrop inside it. The brain pulses and bursts with electrical activity. Different sensations, different emotions, different kinds of thought light up different regions. The brain is a staggeringly complex network. More than 80 billion neurons with trillions of interconnections. Signals triggering new signals that cascade throughout the network. Electrical activity surging and cycling, building up and dying away in patterns that shift and reform, moment by moment. The secret of the mind, it turned out, was not a soul sitting in a chamber somewhere. It was electricity, structure, complexity, and perhaps most importantly, organization. And this is where the concept of emergence becomes critical, because consciousness appears to be an emergent phenomenon, something that arises from the staggering complexity of the brain's neural network, something that cannot be reduced to any single neuron or any single connection, something that is more than the sum of its parts, in the same way that the wetness of water is more than the sum of the behaviors of individual water molecules. Emergent phenomena are all around us, and they are not mystical or supernatural. They are simply properties that appear when large numbers of simple components interact in complex ways. A single ant following a simple set of rules, responding to chemical signals left by other ants, does not organize anything. But a colony of 100,000 ants following the same simple rules produces astonishingly complex behavior. Organized foraging, efficient nest construction, coordinated defense, even agriculture. No single ant is in charge. No ant understands the big picture. The complex behavior emerges from the collective. There is a famous story about a Soviet aide visiting London in the 1980s. He wanted to find the person who organized the bread production in the city. In the Soviet system, bread production was centralized, every step controlled by a single authority. But in London, there was no bread czar.
Nobody coordinated the bakers and the flour mills and the delivery trucks. And yet the bread was there, fresh every morning in bakeries and shops across the city. The bread supply had emerged from the actions of thousands of individual workers, each following their own incentives without any central planning. Some physicists and neuroscientists believe consciousness works along similar lines. Not the product of any single neuron, not housed in any particular brain region, but the emergent result of the entire network working together. The whole vast, interconnected, dynamically self-organizing system of 80 billion neurons somehow gives rise to awareness, to experience, to you. If this is true, then consciousness is a physical process, an extraordinarily complex one, but physical nonetheless. And that means it is made of the same strange stuff we have been talking about all night. Atoms that are mostly empty space, quantum probability waves, vibrations in fields, space-time that bends and stretches. The thoughts you are having right now, this very experience of listening and understanding and wondering, are encoded in the firing patterns of neurons that are made of atoms, that are made of quarks and electrons, which are vibrations in quantum fields, existing in a space-time that is curved by gravity and may be woven from fundamental loops or encoded in some mathematical structure we have not yet discovered. You are a pattern, a process, a particular organization of matter and energy that persists while the material flows through it, like a whirlpool in a river that keeps its shape while the water rushes through, or a flame that maintains its form while the molecules it burns are constantly being replaced by new ones drawn from the air. And the particular pattern that is you, the specific configuration of neurons and connections and electrical activity that constitutes your consciousness at this moment, is unique. There has never been exactly this pattern in the history of the universe. There probably never will be again. The atoms are ordinary, the same kind of atoms that are in rocks and rivers and stars. But the way they are arranged right now in your brain has never happened before. And consider this: the experience itself, the subjective quality of what it is like to be you, is something that no one else can ever access. The philosopher Thomas Nagel wrote a famous essay asking what it is like to be a bat. Bats perceive the world through echolocation, bouncing high-frequency sounds off objects and listening to the echoes. They construct a picture of the world from sound, not light. We can study the neuroscience of bat echolocation. We can map every neuron, trace every signal, understand every mechanism. But we can never know what it feels like from the inside. We can never experience the bat's experience. And the same is true of you. Your experience of the color red, the subjective quality of what redness looks like to you, is something that no amount of neuroscience can capture from the outside. Two people can look at the same red apple and agree that it is red, agree on the wavelength of light, agree on the neural pathways activated, agree on the word to describe it, and still have no way of knowing whether their inner experiences of redness are the same. You cannot prove that what you see as red is the same experience as what someone else sees as red. You can only agree on the label. This gap, the gap between the objective third-person description of the brain and the subjective first-person experience of consciousness, is what philosophers call
the hard problem of consciousness. And despite decades of work by some of the most brilliant minds in neuroscience and philosophy, no one has solved it. We can explain how the brain processes information, how it recognizes faces and plans movements and forms memories. But we cannot explain why all that processing is accompanied by an inner experience. Why is there something it is like to see red rather than nothing? Why does information processing in the brain give rise to the light of awareness rather than happening in the dark? You are unprecedented. And the fact that you are aware of this, the fact that the universe has organized itself, over 14 billion years of expansion and cooling and gravity and chemistry and evolution, into a pattern of matter that can contemplate its own existence, wonder about the nature of time, ask what reality is made of, and feel the weight of a blanket while doing so, this remains one of the most astonishing things that we know about existence. But is the emergent picture the whole story? Some physicists have pushed further. Roger Penrose, the Nobel Prize-winning mathematical physicist, and Stuart Hameroff, an anesthesiologist, have proposed a radical theory called orchestrated objective reduction, or ORC-OR. According to this theory, consciousness does not emerge from classical neural activity alone. It emerges from quantum computations happening inside tiny structures within your neurons called microtubules. Microtubules are hollow tubes made of protein, part of the internal scaffolding that gives cells their shape. They are present in almost every cell in your body, but they are particularly abundant in neurons. Penrose and Hameroff suggested that these microtubules could serve as quantum computers, performing computations that exploit the strange properties of quantum mechanics, superposition, entanglement, and wave function collapse to generate conscious experience. The idea was initially met with deep skepticism. The brain is warm, wet, and noisy, the opposite of the conditions typically needed for quantum effects to survive. Quantum coherence, the delicate state in which a system maintains its quantum properties, was thought to be impossible at body temperature. It would be like trying to hear a whisper in a hurricane. But then, researchers studying other biological systems discovered that nature had found ways to exploit quantum effects at room temperature. Photosynthesis, the process by which plants convert sunlight into energy, was found to use quantum coherence to explore all possible energy transfer paths simultaneously, achieving near-perfect efficiency. The navigation systems of some birds appear to rely on quantum entanglement in certain eye proteins to sense the magnetic field of the Earth. Even our sense of smell might involve quantum tunneling, particles passing through barriers that classical physics says should be impenetrable.
Suddenly, the idea that the brain might harbor quantum processes did not seem quite so far-fetched. And then, experimental evidence began to emerge. Researchers shined light into microtubules and observed quantum coherence lasting far longer than classical physics would predict. Other studies found that microtubules could maintain quantum states for surprisingly long durations. Studies at Trinity College Dublin reported signals from living human brains that were consistent with quantum entanglement. These findings are still debated. Many neuroscientists remain skeptical. The evidence is preliminary, and the leap from quantum effects in microtubules to consciousness arising from those effects is a large one. But the research is ongoing, and the question remains genuinely open. And then there are ideas that go further still. Panpsychism is the philosophical position that consciousness is not limited to brains, that it is not something that only appears when matter is organized in one very specific way. Instead, panpsychism suggests that consciousness, or something like it, some very rudimentary form of inner experience, is a basic feature of reality, woven into the fabric of the universe at every level. That every particle, every atom, Every system possesses it in some form. This might sound absurd, and to most physicists it is. Philosophers have been drawn to panpsychism as a way of addressing the hard problem, the question of why physical processes should give rise to subjective experience at all. But physicists tend to feel that this is well beyond the bounds of what they would call science, at least with current tools and theories. Still, panpsychism points to the depth of the mystery. We do not understand consciousness. We do not know how it arises from physical processes. We do not know why there is something it is like to be you.
And until we do, the question of what makes you you remains wide open. Maybe you are the pattern, the particular arrangement of matter and energy and information that is you, persisting while the material flows through. Maybe consciousness is what it feels like to be a sufficiently complex, self-referential pattern processing information about itself and its environment. Maybe the self is a process, a verb, not a noun. Or maybe there is something more. Maybe there is a role for quantum mechanics in consciousness that we have not yet understood. Maybe the mystery of experience is tied to the mystery of measurement, the mystery of why quantum waves collapse when they are observed. Maybe consciousness and quantum mechanics are connected in ways that will only become clear when we have a theory that unifies gravity and the quantum, a theory of everything that we have been chasing for a century. These are open questions. They are among the deepest open questions in all of science.
And tonight, lying here in the dark, you are participating in them, simply by being aware, simply by being you. Let us go a little further into the dark, because there is one more idea we need to visit before we rest, one more layer to peel away, and it is perhaps the strangest of all. Imagine that the universe is very, very old. Not 14 billion years old, which is its current age, but unfathomably older. Trillions of years. Trillions of years. So old that every star has burned out, every black hole has evaporated, every atom has drifted apart from every other atom, and the cosmos is nothing but a vast, cold, dark, empty expanse, stretching out in all directions forever. This is what physicists call the heat death of the universe. It is the state of maximum entropy, the state in which all useful energy has been degraded into useless warmth, spread evenly across the cosmos, and nothing interesting can ever happen again. No stars, no planets, no chemistry, no life.
Just emptiness and silence, extending into eternity. You might think that this is the end of the story, that after the heat death nothing will ever happen again. But the laws of thermodynamics, the laws that describe the flow of energy and the growth of entropy, are statistical in nature. They are about probabilities, not certainties. And in the realm of probabilities, even the seemingly impossible can eventually happen, if you wait long enough. Ludwig Boltzmann was one of the most insightful minds of 19th century science. Before it was widely accepted, he championed the atomic hypothesis, the idea that matter is made of tiny, indivisible particles. And he recast the laws of thermodynamics in terms of the statistics of these invisible atoms, showing that the tendency of things to go from order to disorder, the increase of entropy, was not a rigid command, but a statistical tendency.
A tendency so overwhelmingly strong that in practice it looks like an iron law, but in principle it could be violated by chance. Boltzmann paid a heavy price for his insights. In the late 19th century, the very existence of atoms was still controversial. Many prominent physicists and philosophers rejected the atomic hypothesis, arguing that atoms were a convenient fiction, a mathematical tool that did not correspond to anything real.
Boltzmann spent years defending his statistical approach to thermodynamics against fierce critics, particularly the Austrian physicist Ernst Mach, who dismissed atoms as metaphysical nonsense. The constant battle wore Boltzmann down. He suffered from depression and poor health. In 1906, while on vacation with his family in the Italian town of Duino on the Adriatic coast, he hanged himself. He was 62.
Just a few years later, experiments confirmed the existence of atoms beyond any reasonable doubt, vindicating everything Boltzmann had fought for. The confirmation came too late for him. But his ideas, the statistical interpretation of thermodynamics, the connection between entropy and probability, the arrow of time as a statistical tendency rather than an absolute law, these ideas became the foundation of modern statistical mechanics and transformed our understanding of the universe. And the concept of entropy, the measure of disorder, the quantity that Boltzmann connected to probability, turns out to be deeply connected to the question of time. Because entropy is the reason time has a direction at all. Think about it. The fundamental laws of physics are time-symmetric. Newton's laws, Maxwell's equations, Schrödinger's equation, Einstein's field equations, all of them work just as well backward as forward.
If you filmed a billiard ball collision and played the film in reverse, the reversed version would obey Newton's laws perfectly. There is nothing in the fundamental equations that distinguishes past from future. And yet, we experience time as having a clear direction. Eggs break, but do not unbreak. Coffee cools, but does not spontaneously heat up. People age, but do not grow younger. There is a clear arrow pointing from past to future, from order to disorder, from low entropy to high entropy. Boltzmann explained this. The arrow of time is not written into the basic laws. It is a consequence of the initial conditions. The universe started, for reasons we do not fully understand, in a state of extraordinarily low entropy, a state of incredible order and organization. And ever since, entropy has been increasing. Things have been getting more disordered. And that is what we experience as the flow of time. The past is the direction of lower entropy.
The future is the direction of higher entropy. Time flows from order to disorder, from the Big Bang to the heat death. And the reason is not a law. It is a boundary condition, a starting point. Think about the air in the room around you. Molecules of nitrogen, oxygen, and carbon dioxide are whizzing about, colliding with each other, with the walls, and with you. At every moment, every configuration of atoms seems completely indistinguishable from any other. The atoms are spread evenly throughout the room, as you would expect. But Boltzmann pointed out that there is no law that prevents all the air molecules from spontaneously gathering in one corner of the room, leaving the rest of the room in a vacuum. The probability of this happening is absurdly small, so small that the word unlikely does not begin to capture it. If you waited a time equal to many trillions of trillions of trillions of times the current age of the universe, it might happen once. But if there is one thing the future cosmos will have in abundance, it is time. In the heat death, with the universe in its maximum entropy state, fluctuations will still occur. Particles will occasionally clump together by pure chance. Most of the time, these fluctuations will be tiny and meaningless, a few atoms drifting together before drifting apart again. The universe goes back to being quiet. But very rarely, much less often, fluctuations will produce something more substantial, a molecule, a complex structure, and vanishingly rarely, unimaginably rarely, but inevitably given infinite time, a fluctuation will produce something with the complexity of a human brain. A brain complete with neurons, complete with connections, complete with patterns of electrical activity, complete with memories, experiences, and the sensation of being alive.
This flickering mind would appear out of nothing,
Experience a brief flash of consciousness, maybe a single thought, maybe the memory of eating an apple or watching a sunset, and then dissolve back into the randomness from which it came. Gone in an instant. The briefest possible spark of awareness in an ocean of emptiness. These hypothetical minds are called Boltzmann brains, and they pose a serious problem for cosmology. Here is why. If the universe goes on forever, and if thermal fluctuations keep happening for all of eternity, then the total number of Boltzmann brains that will ever flicker into existence vastly outnumbers the total number of real, evolved, biological humans who will ever live. By an enormous margin. By an infinity to one margin.
And if you pick a random conscious observer from the set of all conscious observers who will ever exist in the history of the universe, the overwhelming probability is that you will pick a Boltzmann brain, a momentary fluctuation with false memories, floating in the void of a dead universe. So how do you know that you are not one? You are lying here right now with memories of your life, memories of your childhood, memories of what you ate for dinner. Everything feels real, everything feels consistent, but a Boltzmann brain would feel the same way. It would have the same memories, the same sense of reality, the same conviction that it is a real person in a real universe. It would not know that it had popped into existence a nanosecond ago with a full set of fabricated memories about to disappear back into the void. Before you spiral into existential crisis, take a breath. Because here is the important thing. Most physicists do not think you are a Boltzmann brain.
The very consistency of your experience. The fact that your memories cohere. The fact that the laws of physics seem to apply consistently around you. The fact that you can make predictions about the future and have them come true. All of this is evidence that you are a real person in a real universe, not a momentary fluctuation. A Boltzmann brain that happened to have consistent memories and experiences matching the laws of physics would be an enormously more improbable fluctuation than a generic Boltzmann brain with random, incoherent impressions. The odds of a random fluctuation producing a brain with your specific, self-consistent set of memories, memories that match the actual history of the universe as we understand it, are so much lower than the odds of producing a generic momentary brain that the real person explanation wins overwhelmingly. But the Boltzmann brain scenario is not just a philosophical scare.
Physicists take it seriously because it serves as a test for cosmological theories. If your theory of the universe predicts that Boltzmann brains will outnumber real observers, then your theory has a problem. It is predicting that you are most likely something you clearly are not. And that means the theory is wrong, or at least incomplete. This test has real consequences. It constrains the possible futures of the universe, the nature of dark energy, the ultimate fate of the cosmos. The fact that you are here, coherent and consistent, and not dissolving into randomness, tells physicists something about the structure of the universe. Your existence, your continuity, your coherence, is a piece of evidence about the nature of reality. And there is a deeper version of this argument. Max Tegmark's mathematical universe hypothesis, the idea that every self-consistent mathematical structure exists as a universe, faces the Boltzmann brain problem head-on. In an infinite mathematical multiverse, the number of brief, flickering mathematical structures that resemble a conscious mind for an instant would vastly exceed the number of structures that correspond to a full, evolving universe with stars and planets and evolution. So if you take the mathematical universe seriously, you have to explain why you seem to be in a universe with a 14 billion-year history, consistent laws, and a coherent past, rather than being a momentary mathematical fluctuation. These are live questions in modern cosmology. They are not settled. The relationship between consciousness, entropy, time, and the mathematical structure of the universe remains one of the great open frontiers in physics. And at the heart of all of them is the same question we started with tonight. The question about you. The question about what persists, what is real, what makes you the same you from one moment to the next, in a universe where everything is in flux, everything is impermanent, everything is built on foundations that turn out, when you look closely enough, to be made of nothing solid at all. So let us gather the threads, all of them. Let us bring this journey to a close here, in the dark, with the weight of the blanket and the slow rhythm of your breathing. We started with your body, and we discovered that it is constantly replacing itself. Your blood cells live 4 months. Your skin cycles every few weeks. Your bones take about 15 years. Almost every atom in your body will be replaced by different atoms within a decade. The material you are made of is not permanent. It flows through you like water through a riverbed. We went deeper, to the atoms themselves, and we discovered that they are not what they seem. An atom is mostly empty space. If you scaled one up to the size of a football stadium, the nucleus would be a marble on the 50-yard line, and the electrons would be gnats in the upper decks. The solid feeling of the world is maintained by electromagnetic forces between neighboring electron clouds. Your hand never actually touches the table. We went deeper still into the quantum world, and we found that the particles inside your atoms are not really particles. They are probability waves, spread out over space, not located in any definite position until they are measured. The double slit experiment showed us that a single electron can pass through 2 slits at once, interfering with itself like a wave, yet landing on a screen as a definite point. Born's interpretation told us that the quantum wave is a wave of probability, and the act of measurement collapses it into a definite outcome. We saw that reality is non-local, Bell's theorem, and decades of increasingly precise experiments have shown that entangled particles share a connection that transcends space. Measuring one instantaneously determines the state of the other, no matter how far apart they are. The universe is not a collection of separate, independently existing objects. We turned to time, and we found that it is not the steady, universal flow that Newton imagined. Maxwell's equations revealed light as electromagnetic waves, and their refusal to specify a rest frame led to the Michelson-Morley experiment, which found nothing, and to Einstein's 2 postulates, which dissolved everything. Simultaneity depends on the observer. Moving clocks run slow, time dilates. We saw the evidence. Muons that should decay in mid-air reaching the ground because their clocks run slow. Atomic clocks on airplanes disagreeing with clocks on the ground. GPS satellites requiring relativistic corrections that amount to 10 kilometers of drift per day if ignored. We followed Einstein through the happiest thought of his life. The equivalence of gravity and acceleration, through a decade of agonizing mathematical struggle, to the triumph of general relativity in 1915. Gravity is the curvature of spacetime. Mass tells spacetime how to curve, and spacetime tells mass how to move. And gravity bends time. Near massive objects, time slows down. Your feet age slower than your head. Black holes warp time to its extreme. We confronted the block universe, the idea that past, present, and future all exist simultaneously as a static 4-dimensional structure, with no flowing time, no special now. And we considered the alternative, loop quantum gravity, where space-time is woven from fundamental loops, where the past is the finished tapestry, and the future is the unwoven thread, and the present is the busy, active edge
where reality is being constructed. We looked at the deepest layer, quantum field theory, where particles are vibrations in fields that fill all of space. The electron field, the quark fields, the electromagnetic field, the gluon field, the Higgs field, all singing together. You are made of these vibrations. You are a chord played on quantum fields. We saw that symmetry is the skeleton of reality, that conservation laws follow from symmetries, and that the universe exists because those symmetries are cracked. The tiny asymmetry between matter and antimatter, 1 part in a billion, left behind the surplus of matter that became everything. We explored the mystery of consciousness and the open question of whether it is purely emergent, arising from the complexity of neural networks, or whether quantum mechanics plays a role through structures like microtubules. We visited the hard problem of consciousness, the question of why there is something it is like to be you, and we admitted that we do not have an answer.
And we visited the Boltzmann brain, the flickering mind in the dead universe, and saw that your coherence, your consistency, your ability to read this and understand it and remember it tomorrow is itself evidence that you are real, that your past is real, that the universe you inhabit is real and not a random fluctuation. So, after all of that, after peeling away layer after layer, each revealing something stranger than the last, what is left? You are. You are made of atoms that are mostly empty space, held together by electromagnetic forces described by probability waves in quantum fields. The particles that make up those atoms do not have definite properties until they interact with something. They are entangled with particles across the cosmos. The space-time in which you exist bends and stretches, runs at different rates depending on gravity and motion, and may be woven from fundamental quantum loops at scales far too small for any instrument to see.
Your body is replacing itself, constantly, silently, cell by cell, atom by atom. The material is impermanent, but the pattern persists, the organization persists, the process persists. You are not a thing, you are a happening. You are something the universe is doing right now, in this place, through the particular arrangement of fields and forces that is your body and your brain. And the particular way the universe is doing you, the specific pattern of matter and energy and information that constitutes your consciousness at this moment, is unique in all of cosmic history. It has never existed before. It will never exist again in exactly this form. The atoms are ordinary. The fields are the same fields that fill the space between galaxies, but the arrangement is yours alone. You are a once-in-a-universe event. The Ship of Theseus is still the Ship of Theseus, not because the planks are the same, but because the voyage never stopped. Your breathing has slowed now. You can feel it. The rhythm of your chest, the rise and fall, has settled into something deeper and more even than it was when we began. The room around you is dark. The sounds of the outside world have faded, or maybe they are still there, but they matter less now, receding to the edges of your awareness like distant stars at the edge of the visible universe, still real but too far away to demand your attention. Your body is doing its quiet work. The millions of red blood cells that died while we were talking have already been replaced. Your skin is renewing itself, invisibly, gently, cell by cell. The atoms in your muscles, in your bones, in the tissues of your heart are being slowly, silently swapped out, exchanged for atoms drawn from the last meal you ate, the last glass of water you drank, the last breath you took. You are being rebuilt, right now, in this moment, as you lie here.
The process that is you continues, as it has continued since the moment you were born, as it will continue until the moment it stops. And
and the space-time around you is gently curved. Not dramatically, not noticeably, but measurably, if you had instruments sensitive enough. Gravity is bending time around your body, the way a stone in a river bends the current. Your feet are aging a trillionth of a second slower than your head, every second. The geometry of the universe is responding to the small, warm mass of your body, curving ever so slightly, a quiet acknowledgement from the cosmos that you are here, that you are real, that your presence registers in the structure of space-time itself. The quantum fields that make up your body are still vibrating. The electrons in your atoms are still behaving as probability waves, spread out in their orbitals, entangled with other particles in ways that no one fully understands.
The quarks inside your protons and neutrons are being held together by gluons, bound by the strong force, their quantum fields humming like a low chord that never resolves and never stops. Your neurons are still firing, slower now as sleep approaches, but still firing, still forming patterns, still maintaining the process that is you. The 80 billion of them, with their trillions of connections, are settling into the rhythms of rest. As you drift towards sleep, the character of your brain's electrical activity changes. When you are awake and alert, your neurons fire in fast, irregular, desynchronized patterns, each one going about its own business, responding to the world, processing information, making decisions. But as sleep approaches, the patterns begin to synchronize. Large populations of neurons start firing together in slow, rhythmic waves that sweep across the cortex like ocean swells rolling across the surface of the sea. These are called slow-wave oscillations, and they are one of the deepest mysteries of neuroscience. During these slow waves, your cortex alternates between states of activity and silence, up states and down states, roughly once per second. In the up states, neurons fire vigorously, exchanging information, replaying fragments of the day's experiences, consolidating memories. In the down states, the neurons go quiet, all of them together, a synchronized silence that washes over the brain like a wave. Nobody fully understands why the brain does this, but it seems to be essential for memory consolidation, for emotional processing, for the maintenance of the neural networks that hold your identity together. Sleep is not a passive state. It is not your brain shutting down. It is your brain doing something specific and important, reorganizing itself, strengthening some connections and pruning others, integrating new experiences into the existing structure of your memories and personality.
So when you wake up tomorrow, you will be subtly different. Not just because some atoms have been swapped out, not just because some cells have been replaced, but because the connections between your neurons will have been reshaped by the slow waves of the night. The process that is you will have been maintained and updated, like software receiving a patch while the machine is in sleep mode. And when you wake up, you will be the same you. Not because the atoms are the same, not because the cells have stayed put, but because the process continued, unbroken, through the night. The pattern persisted. The flame kept burning. The ship kept sailing. The universe has been doing this for 14 billion years, making patterns, maintaining them for a while, letting them dissolve, making new ones. Hydrogen atoms, the simplest things in the universe, just one proton and one electron, coalesced out of the cooling plasma of the Big Bang, about 380,000 years after the beginning. Gravity gathered these atoms into vast clouds, and the clouds collapsed under their own weight, squeezing the hydrogen until the cores ignited and the first stars were born. These early stars were enormous, hundreds of times more massive than the Sun, burning through their fuel in just a few million years. And when they died violently. in supernova explosions that outshone entire galaxies for a few weeks, scattering the heavy elements they had forged in their cores: carbon, oxygen, nitrogen, iron, calcium, across space. Those atoms drifted for millions of years, mixing with the interstellar gas until gravity gathered them again into new clouds, new stars, new solar systems.
Our Sun formed about 4.6 billion years ago from one such cloud, and the leftover material formed the planets, including the Earth. The atoms in your body were forged in several different stars over billions of years. The calcium in your bones might have been made in a star that exploded 7 billion years ago. The iron in your blood might have come from a different star in a different part of the galaxy that exploded 5 billion years ago. You are an assembly of stardust from multiple sources, gathered by gravity, organized by chemistry, animated by evolution. Life emerged from this chemistry about 3.8 billion years ago in ways we still do not fully understand. Single-celled organisms appeared first, thriving in the warm oceans of the young Earth. For billions of years, life remained microscopic. Then, about 540 million years ago, in the Cambrian explosion, multicellular life burst onto the scene in a riot of forms and body plans.
Evolution produced fish, amphibians, reptiles, mammals, primates, and eventually a lineage of upright walking apes in Africa whose brains grew larger and more complex over millions of years, until one species developed language, art, mathematics, and the ability to wonder about the nature of the universe. That species is you. And the fact that the universe produced you, that it took hydrogen atoms and turned them into stars, and turned the ashes of stars into planets, and turned the chemistry of planets into biology, and turned biology into brains, and turned brains into awareness, is one of the most astonishing sequences of events that we know of. You are one of those patterns, a brief one by cosmic standards. A human life is a flicker, a spark, a single frame in a film that has been running for 14 billion years and will run for trillions more. 80 years, maybe 90, maybe 100, against a backdrop of billions. The asymmetry is staggering. The universe existed for 10 billion years before the Earth even formed, and it will go on for trillions of years after the last star burns out. But it is your flicker. It is your spark. And no other pattern in the history of the universe, no other arrangement of matter and energy and quantum fields has ever been or will ever be exactly like you. The particular way your neurons fire, the particular memories you hold, the particular way you see the world and feel the world and move through it. All of this is a one-time event, a unique configuration of the cosmos that will never be repeated. And the fact that you can appreciate this, the fact that the universe has produced a pattern complex enough to contemplate its own impermanence and find wonder in it, suggests that the universe, through you, is doing something rather unusual. The atoms will move on.
After you are gone, the carbon in your bones will become part of the soil, and then part of a plant, and then part of the air, and then part of a cloud, and then part of an ocean, and then part of something else, something unimaginable, something that does not yet exist and will not exist for millions of years. The atoms do not care. They have no memory. They will cycle through the universe, being part of one thing after another, for as long as there are things to be part of. But the pattern was yours. The process was yours. The experience was yours. And for a little while, in one small corner of one small galaxy, the universe knew itself through you. So let your eyes close.
Let the thoughts slow down. Let the questions settle, like sediment drifting down through dark water, finding the bottom, resting there. You do not need to hold on to any of it. Not the atoms, not the waves, not the fields, not the space-time, not the block universe, or the edge of the weave. It will all be there in the morning. The physics will not change while you sleep. The quantum fields will keep vibrating. The space-time will keep curving. The muons will keep raining down from the sky, living their dilated lives, reaching the ground. And you will keep being you. The process will continue. The pattern will hold. The ship will sail on through the night, and you will wake up on the other side. The same you, made of different atoms, carried forward by the same ongoing, extraordinary, unrepeatable process that has been you since the beginning. Sleep well. You are a pattern in the fields, a vibration in the quantum fabric, a brief and improbable arrangement of matter that knows it is matter. And that is, in its own quiet way, one of the most unlikely things the universe has ever done. Notice your breathing, the rise, the fall, the tiny pause at the top, the tiny pause at the bottom. Each breath pulls in atoms that were recently part of the atmosphere, part of the wind, part of the exhalation of trees and oceans and other people on the other side of the world. And each breath pushes atoms back out, atoms that were, for a brief moment, part of you. Your boundary with the world is not sharp, it is porous. You are constantly exchanging material with everything around you, breathing in the universe and breathing yourself back out into it. And right now, somewhere above you, muons are falling from the sky. Created 15 kilometers up in the upper atmosphere by cosmic rays that have been traveling through interstellar space for millions of years. They are moving at nearly the speed of light, their internal clocks running slow, their lifetimes stretched by special relativity, surviving far longer than they should. They are passing through the roof above you, through the ceiling, through your body, at this very moment. Tiny ghosts of time dilation raining down on you from the cosmos. You cannot feel them. You will never know they are there. But they are there, and they are evidence, physical, measurable evidence, that time is not what it seems. And in the nucleus of every atom in your body, quarks are being bound together by gluons, held in place by the strong force, vibrating in their quantum fields. And the electrons in your atoms are spread out in their probability clouds, not quite here, not quite there, existing as smears of likelihood until something forces them to choose. And the Higgs field is giving mass to every particle in your body, an invisible molasses filling all of space, present right here, right now, between you and the mattress, between you and the pillow, between you and the dark. You do not need to understand any of it to be it. You do not need to comprehend the Schrödinger equation to be a solution to it. You do not need to grasp general relativity to curve space-time. You are already doing all of these things simply by lying here, simply by being a collection of matter in a gravitational field, simply by being alive. The atoms will still be dancing in the morning, the space-time will still be gently curved, and you, whatever you are, will still be here. Sleep. Let the questions settle. Let the layers fold back over each other like petals closing for the night. You have looked deeper tonight than most people ever will, down through the cells that are constantly replacing themselves, through the atoms that are mostly empty space,
through the quantum probability waves that shimmer at the heart of matter, through the entangled connections that link particles across the cosmos, through the curvature of space-time that bends the flow of time around every mass in the universe, through the quantum fields that vibrate with the music of existence, through the broken symmetries that made matter possible, through the mystery of consciousness that remains unsolved, through the Boltzmann brains that flicker in the void of eternity. And what you found at the bottom was not emptiness. It was not nothing. It was a process. It was a pattern. It was you. Good night.